be live at some stage. Do a bunch of things today. Should be live. Have too many windows open. What's up with the stream? Okay, we should be live. Oops. Didn't intend to do that. Okay, I'll start in a sec if you let me know if you've seen the website before. Okay. Yeah, this link, the slash category neurological doesn't always work in all places. So if I give it to Gemini, for example, it can't actually use the category information. So I don't know what's up. What's up with that? Anyway, we're doing deep research onto this injectable device. We probably should look into the difference between what is it, implantables, injectables, insertables, injectables, implantables. What else there is? What else there is? And apparently, so we have this prompt engineer that we're using. But apparently, we're using the wrong one. We were using the wrong prompt engineer. Well, because they keep changing stuff. So you have Flash Live, Flash Preview, 2.5 Preview. Okay, the names obviously are not great, but the two new ones, yeah, there's an expert and a non-expert. So there's a thinking and non-thinking. Let's actually try thinking real quick. And oops. Okay, bear with me. I lost. The window. Let's have it on another page. Hey, what do you see on the screen? Okay, and what are you looking at? What's currently on the screen? Hey, oops. Had the audio off. 1 sec. I'm not sure which one we should be. using. We have these questions. Someone posted on LinkedIn, obviously about data science, so I'm not an expert, pretending to be a data science expert, but we do have an expert. Hey, what do you see on the screen? Can you not answer the question, but just guide me, give me a clue?
It looks like you're looking at information about a new technology for a common sleep problem. It involves a small implanted device.
Okay, oops. Oops, daisy. Okay, can you just tell me what's on the screen? Don't answer the question, just tell me what's on the screen.
The screen shows a question labeled Question 1. The question asks, what is the primary purpose of cross-validation in machine learning? Below that, there are 4 options. A, to increase the size of the training dataset. B, to reduce computational complexity. C, to assess model performance and reduce overfitting. D, to automatically select features.
Okay, and what's the answer?
The answer is C, to assess model performance and reduce overfitting.
Can you explain the answer?
Cross-validation is a technique used to evaluate the performance of a model on unseen data. It helps to assess how well the model generalizes and to prevent overfitting, which is when a model learns the training data too well and performs poorly on new data. Options A, B, and D are not the primary purpose of cross-validation.
Hey, can you explain it without using any jargon to someone who is not an expert?
Okay, think of it like testing a student. Instead of just giving them one big test, you give them several smaller tests using different parts of the material they studied. Cross-validation does the same thing with data. It helps make sure the model can work well on new information too, not just what it learned from the initial data, so it can avoid making mistakes on new problems.
Okay, can you explain this question and oops and and give me the answer?
Okay, so the question is asking how to classify samples based on probabilities given by a model. Imagine the model gives a score for each sample, a probability between 0.
Keep going. Yeah, it's thinking for too long. It's the Gemini 2.5 Flash Experimental Native Audio Thinking Dialogue. So it just takes too long to respond. Okay, let's try different. Let's try a different model.
Based on the question, a logistic regression model outputted the probabilities of 0.8, 0.9, and 0.1 for 4 test samples. Using a threshold
Okay, we're having issues.
I understand. Using a
Can you just answer the question?
Certainly. Using a threshold
Oh, come on.
Apologies for the confusion. Given the probabilities of 0.8, 0.9,
Can't finish a response. Okay, that let's close that for a sec. Let's control F5 Gemini. Let's do 66 tokens. Session context. So it's not doing a search or anything, just using the model itself. Hey, can you look at the question on the screen and answer what's the correct option?
The correct option is A.
Are you sure?
Yes.
It's okay, what model? What model are you?
I am a large language model trained by Google.
Okay, let's try. Let's go back to the experience. It's a thinking. Let's go to a thinking model real quick. Let's do back again. Sharing the screen. Can you answer this question on the screen?
The predicted classes using a threshold.
Keep going. Actually answers it correctly. But yeah, it's like the combining the things, like the speech, the conversational model. Yeah, I don't know why combining them is such a... So it's still like thinking. It's obviously finished thinking. It says the answer is B. Okay, can you answer now?
Okay. The predicted classes using a threshold of 0.5 would be 1, 0, 1, 0. So the correct answer is option B.
And can you explain it to without using any terminology?
Sure. Imagine you have 4 scores, 0.8, 0.9, and 0.1. You use a cutoff point.
Yeah, keep going.
Which is 0.5. If the score is higher than the cutoff, you assign one label, like 1. If it's lower, you assign another label, like 0. So for your scores, 0.8 is above the cutoff, so it gets a 1. 0.3 is below, so it gets a 0. 0.9 is above, getting a 1. And 0.1 is below, so it gets a 0. That's how you get the sequence of labels.
Okay, that's actually correct. How about this one?
The correct answer is D. The training accuracy is not a hyperparameter. It's a measure of how well the model performs after training, not a setting you choose beforehand.
Again, can you explain it to a layperson?
Think of hyperparameters like the settings you adjust before you start building your model, like how many trees to use or how deep they should be. Training accuracy, on the other hand, is like the result or score you get after the model has learned. It tells you how well it performed, but it's not a setting you choose in advance.
Okay, how about question 4?
The term curse of dimensionality refers to option B, the exponential increase in data sparsity as dimensions increase.
Okay, can you explain it to a layperson?
Imagine you're trying to find something in a small room versus a giant stadium. The small room has fewer places to look, making it easy. The stadium is huge, and even with the same amount of stuff, everything gets spread out much more. The curse of dimensionality is like that. When your data has many different characteristics, it's like being in a giant stadium, and it gets really hard for computers to find meaningful patterns or connections between things because the data is so spread out.
Can you explain it without any terminology?
It's like trying to find something in a small room versus a huge stadium. In the small room, things are close together and easy to find. But in a giant stadium, everything gets spread out really far, making it much harder to find or connect things. The curse of dimensionality is like that. When your data has many different characteristics, it becomes really difficult for computers to find meaningful patterns because the data is so spread out in that vast space of characteristics.
Can you give an example from brainwave recordings from EEG?
Okay, imagine you're recording brainwaves with many electrodes on someone's head. Each electrode gives you a different piece of information, like adding another dimension to your data. With many electrodes and lots of time points, your data becomes very complex and high-dimensional. The curse here means that even with a lot of recordings, the data points become very spread out in this complex space, making it hard for computers to find clear patterns or understand the actual brain activity because the data is so sparse.
What do you mean by sparse in this case?
In this case, space refers to the vast area where your data points exist, defined by all the different characteristics or dimensions, like the readings from each electrode at different times. Sparse means that even with a lot of data,
The individual data points are so thinly across this huge space. It's like having very few people scattered throughout a massive stadium, making it hard to find any groups or connections between them. The data is just too spread out to see clear patterns.
Okay, can we move on to question 5?
The accuracy of this model is 0.85, which is option B. You calculate it by adding the true positives and true negatives, then dividing by the total number of predictions.
Hey, can you explain this without using any terminology?
Accuracy is like checking how many times the model got things right, compared to the total number of guesses it made. You add together the times it correctly said yes and the times it correctly said no, and then divide by the total number of predictions it made. In this case, it correctly said yes 85 times and correctly said no 120 times, so that's 205 correct guesses. It made a total of 240 predictions. So its accuracy is 205 divided by 240, which comes to approximately 0.85, meaning it was correct about 85% of the time. Okay, imagine you have a model that looks at ECG readings to detect heart issues. The true positives are the times it correctly identifies an actual heart issue. The true negatives are the times it correctly says there's no issue. False positives are when it mistakenly flags a normal reading as a heart issue, and false negatives are when it misses a real heart issue, saying it's normal. Accuracy is simply how often it gets both the yes correct and the no correct out of all its predictions. In this case, it was right 85 times for issues and 120 times for normal readings, so it was correct 205 times total. Since it made a total predictions, its accuracy is about 85%.
Can you give an example in ECG, an example of each true positive, false positive, true negative, false negative?
Sure. In an ECG model, a true positive is when the model correctly identifies a heart issue, like an abnormal rhythm, when the person actually has that issue. A false positive is when the model mistakenly says someone has a heart issue when their ECG is actually normal. A true negative is when the model correctly says that there is no heart issue and the person's ECG is truly normal. And a false negative is when the model misses a heart issue, incorrectly saying the ECG is normal when there actually is a problem. Accuracy is just how many of these correct calls it makes out of all its attempts to identify issues.
Okay, can you explain this question?
This question is asking about which algorithm is best for finding groups or clusters in your data when you don't know how many groups to expect. K-means requires you to specify the number of clusters beforehand, but dbScan is different. It finds clusters based on how densely packed the data points are, so you don't need to know the number of clusters in advance. Linear regression and naive Bayes are used for prediction and classification, not for finding clusters. So dbScan is the best option here.
Okay, for a biomedical example, imagine you're analyzing ECG data from patients. You might extract different features from the ECG signals, like certain brainwave patterns. Since you might not know exactly how many distinct patterns exist in the data, you could use DB-Scan. It would group similar ECG feature points together based on their density, identifying clusters of potential different brain states, or pinpointing unusual patterns as noise, without needing to decide how many groups to look for. Okay, think of it like this. You have a bunch of ECG readings from different people, and you want to find groups of similar heart patterns in the data. K-means needs you to tell it upfront how many different types of heart patterns you expect to find, like maybe 3 or 4 distinct groups. DB-Scan, on the other hand, looks for these groups by finding areas where a lot of the ECG readings are very similar, or dense. It doesn't need you to tell it the number of groups beforehand, and it can also identify unusual readings that don't fit into any dense group. So if you're not sure how many different types of heart patterns there are, DB-Scan is a better choice. In gradient descent, the learning rate controls the size of the steps you take towards finding the minimum value of a function. It's like deciding how big of a jump you make each time you're trying to go downhill. So the correct answer is C, the size of steps taken toward the minimum.
Imagine you're trying to find the lowest point on a hill, and you're taking steps to get down. Gradient descent is like following the steepest path downwards. The learning rate is simply the size of each step you take. If the learning rate is large, you take big steps, which might get you down quickly, but you might overshoot or bounce around. If it's small, you take tiny steps, which might take longer but are more likely to find the exact lowest spot. For example, when training a model to detect heart issues from ECG data, the learning rate determines how much the model adjusts its internal settings each time it makes a prediction. A high rate means big adjustments, while a low rate means small adjustments, in trying to improve its accuracy over time.
Can you give an example from detecting seizures in brainwave recordings, in EEG recordings?
Okay, think of the learning rate as how much the model changes its understanding after looking at each ECG recording. If the learning rate is high, the model makes big changes quickly based on each example. This can make it learn fast, but it might also jump around too much and miss the best way to detect seizures accurately. If the learning rate is low, the model makes very small, careful adjustments each time. This makes the learning process slower, but it's more likely to find the most stable way to correctly identify seizures without getting confused.
This question is asking about the total number of adjustable parameters in a specific neural network design. The architecture given, 784, 128, 64, 10, describes the number of neurons in each layer. The parameters are the weights connecting neurons between layers, and the bias terms for each neuron. To find the total, we need to calculate the weights and biases for each connection between layers, and sum them up. The calculation involves multiplying the number of neurons in one layer by the number of neurons in the next layer for each weights, and then adding the number of neurons in the subsequent layers for the biases. The correct answer is C, 109,386.
Imagine a neural network like a complex brain with different layers of interconnected nodes. The parameters are essentially the connections between these nodes and the individual settings for each node.
The architecture you described is like saying there's an input layer with 784 nodes, then 2 hidden layers with 128 and 64 nodes respectively, and finally an output layer. Right. So to find the total number of parameters, we calculate the connections between each layer. First, between the input layer and the first hidden layer, there are 784 nodes in the first layer, connecting to 128 nodes in the second, creating 784 times 128 connections or weights. Plus, there's a bias term for each node in the second layer, adding another 128 parameters. Then, between the first and second hidden layers, we have 128 nodes connecting. Right. So to get the total number of parameters, you calculate the connections between each layer. From the input layer to the first hidden layer, there.
Yeah, we're having issues. We are having issues. We are having issues. Well, it answers everything correctly, so 8 out of 8 so far. Just having issues with the model and the prompting. With the model and the prompting. Well, we need the prompt. So if it's a problem with the voice. Can we give an example from biomedical data, specifically brainwave recordings in epilepsy patients? So how would you use this in detecting epilepsy in EEG? Let's see if we can prompt it manually. Will it start talking?
Okay, sure. Imagine this neural network as a system that analyzes EEG recordings from epilepsy patients. The first layer, with 784 nodes, takes in features extracted from the EEG signal, like specific wave patterns or frequencies that might be important. The next 2 layers, with 128,
It's useless. Wait, we have 19 seconds of.
Okay. The next 2 layers, with 128,
It's only generating up to 19 seconds at the time. Okay, can you generate the full response?
Okay, so this question is asking about the total number of adjustable parts in a specific neural network design. Think of the network like a system with multiple layers of processing. The numbers like 784, 128, 64.
Yeah, it's obviously a problem with the speech model. would not generate audio longer than like 20 seconds or so, which is a bit of, yeah, 13 seconds in this case. That's a bit odd. Yeah, because I'm pretty sure, yeah, let's close this for a sec. I'm pretty sure we can, well, the answers are in the PDF in this case. I mean, yeah, we can see if it's actually explaining specific. Okay, we give example. Answer each question. Provide the logic. Explain to a layperson, and then give an example from biomedical data, specifically brainwave recordings in epilepsy patients. So how would you use this in detecting epilepsy seizure in EEG? How does that sound? So pop the whole PDF into Gemini, and obviously use Gemini 2.5 Pro. 2.5 Pro. Give it that document. Need to repeat each question. Okay, I'll pop this PDF, and we have a prompt. Shall we turn it into a canvas? Let's see what it does. Now I'm fully immersed in question 2. Optimal threshold for logistic. Where are the questions? Yeah, this is not going well, is it? Determining optimal threshold. Yes. Yeah, it went full on like agent mode, actually going over the entire PDF. It has 47. We'll let it run. We'll come back to it later on, if you don't mind. Do something else for now, real quick. Let's play a bot for a sec. It's just an overview of what we are doing on this channel from robots, obviously. That's. Can you guess? Can you watch this and guess which one is a real human?
we're making powerful biomedical tools accessible to everyone.
Ever wondered what your brainwaves sound like? Or look like? Ever wanted to play with real scientific tools? Ours are free and open source. You won't believe what you can do with your own data.
Want to dive into data science? Start with our interactive tools.
Go ahead. Play with the data.
It's actually amazing how accurate the ECG in that last video is. Yeah, check this out. Yeah, I don't know. The icons at the bottom of the screen are a bit odd. There's some odd thing there in the corner. Oops, can't see. Yeah, that thing in the corner is a bit odd, but the ECG itself and the sound of it. Boom, 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 boom. It's not messing up the text anymore, so that was solved. What's the sound?
Go ahead.
Yeah, the sound is actually even consistently following the waveform.
Science? Not for tools.
Oh, it's following where the current cursor is. The sound, the ECG waveforms seem to be hyper realistic.
Go ahead. Play with the data.
Right, yeah. So do what the robot said. It's all on BioniChaos.com. If there is a human who wants to ask anything, we can answer any questions about the website. Otherwise, I will move to have some summaries by Notebook LM that we'll listen to and we'll come back to development later on.
Welcome to the Deep Dive, where we take complex topics, cut through the noise, and give you the essential insights you need to be truly well-informed. Today, we're plunging into a world that's becoming increasingly relevant to all of us. The vast, rapidly expanding universe of biomedical data. Think about your own health records, right? Or the incredible scientific discoveries happening daily. This data is really the engine of modern medicine. But, and this is the focus today, it comes with some surprising hidden costs and challenges. Our mission today is to unpack this intricate relationship between privacy, the sheer explosion of health information, and, well, the surprising bottlenecks researchers are facing as they try to make sense of it all. We'll be drawing from a really fascinating stack of sources. We've got a deep dive into biomedical data privacy from PMC, studies on research data management from the Journal of the American Medical Informatics Association, recent insights on genomic data analysis from Nature Reviews Genetics, and a look at patient and public views on data sharing from the Journal of Medical Ethics, plus a recent report on scaling biomedical databases. Quite a mix. So if you've ever wondered how your health data is handled, or what it really takes to power the next big medical breakthrough, you're definitely in for a treat. Okay, let's dive in. So when we talk about biomedical data, privacy is usually the first thing that pops into mind. And it's not new, right? It's been around since the ancient Greeks even, and definitely reinforced with the rise of electronic medical records decades ago. But here's where it gets really interesting. The arrival of ultra-cheap data collection and processing tech is fundamentally changing everything.
It really is. What's truly striking here is how the traditional boundaries of healthcare are just dissolving. We're seeing health information collected everywhere now, mobile devices, obviously, sensors in your own home, even things called body area networks, tiny sensors you wear. And at the same time, the sheer detail and The diversity of information are increasing at an unprecedented rate. You've got your standard clinical data, but now it's complemented by all this omics data like genomics, proteomics, and it paints an incredibly detailed picture.
And with this data explosion comes what our sources call a privacy invasion, which sounds pretty serious. We've seen these troubling cases, right? Healthcare providers snooping on records of famous people or even family and friends.
Yeah, that happens.
And personal info being used for identity fraud. Millions of records exposed because someone lost an unencrypted laptop or phone.
Right. So the natural next question becomes, what's the real-world impact of these breaches? It's not just theoretical. The sources reveal a pretty concerning trend. Patient trust is eroding. I mean, think about this. Between 15% and 17% of U.S. adults have actively changed their behavior to protect their health info.
15 to 17%, that's a lot.
It is. And it's not just worry. It means people are actually going to another doctor, maybe paying out of pocket to avoid insurance records.
Yeah.
Sometimes not seeking care at all to avoid an employer finding out, giving inaccurate information, or even self-treating instead of seeing a provider.
Wow.
And specific vulnerable groups, adolescents, people with HIV, mental health patients, victims of domestic violence, they report similar behaviors. There was one survey, for instance, 15% of Californians said they avoided discussing depression with their primary doctor because of privacy concerns.
That's staggering. It really drives home how deeply personal this data is.
Exactly. The core insight here is that privacy isn't just some abstract legal thing. It's directly impacting public health behavior.
And our sources explain that privacy itself is, well, complex. It's multidimensional. It covers anonymity, confidentiality, solitude, and it's highly contextual, right? Your expectation of privacy is totally different talking to your doctor versus, say, a stranger on the bus.
Absolutely. And even how sensitive you feel specific health information is varies hugely from person to person. To manage this complexity, the journey of biomedical information can be thought of in 3 distinct zones. That's how the sources frame it.
Okay, 3 zones. What are they?
So first is the collection zone. This is where data is first gathered, could be at a clinic, could be via a mobile app. Here, privacy is about who can collect it, how much, when, and for what purpose. It's about anonymity, limiting content, getting consent.
Got it. Collection zone. What's next?
Second is the primary use zone. Once collected, data lives in systems controlled by whoever's providing the primary service, like direct patient care or a specific research project. Here, privacy focuses on confidentiality and security. Who gets access? For what? How is it protected?
Okay, primary use. Makes sense. And the third?
The third is the secondary use zone. This is when data gets used for purposes different from why it was originally collected. Think repurposing clinical data for a totally new research study, or sharing public data sets for policy evaluation.
Okay, so the data takes on a new life, potentially.
Exactly. And this zone brings up unique issues of anonymity and consent, both for individuals and potentially for groups, because the original purpose has shifted.
That framework collection, primary, secondary use, that actually helps clarify things a lot. But how do we actually address the challenges in each zone?
Well, the sources highlight 2 interacting tracks. There's a socio-legal track defining rights, responsibilities, policies, and then there's the technical track building controls directly into the information systems.
Okay, so law and tech working together. Can you give some examples?
Sure. On the socio-legal side, you see things like patients wanting really granular control over their electronic medical records. There are studies looking at how teenagers perceive health privacy on social media, which is a whole new can of worms.
Oh, I bet.
There's the privacy by design framework used in British Columbia for their population data. The U.S. HIPAA de-identification strategy is another example.
Yeah.
There's even a Supreme Court case, Sorrell versus IMS Health, all about selling prescription records. So big legal battles.
Right. And on the technical side?
Technically, HIPAA's security rules specifies safeguards like authorization controls for who can access EMRs. Though, interestingly, encryption of stored health data is technically addressable, not strictly required by HIPAA, which surprises some people.
Oh, it's not required, huh?
Yeah, and a study found that security practices really vary among U.S. healthcare organizations. There's also a significant insider threat. People who should have access may be looking where they shouldn't.
The snooping thing again.
Exactly. So data-driven auditing strategies are being proposed to track who accesses what. We also see de-identified data used a lot for research, like correlating web searches with actual visits to healthcare facilities. And there's even more advanced stuff, like private record linkage, matching records without a central identifier, and deriving secure genomic fingerprints to track patient records anonymously.
So this means really sophisticated methods are being developed, like automatically stripping out names and addresses from text using AI.
Yep, using both rule-based systems and machine learning. And for structured data, like lab results, there are techniques like clinically informed perturbation.
Perturbation, like adding noise.
Exactly. Adding a tiny bit of calculated random noise to, say, lab test results to make it harder to re-identify someone without really affecting the overall research value. Or the K-anonymity principle.
Right, you mentioned that. Where every record looks like at least K other records.
Precisely. So if K is 5, your data, even if unique, is indistinguishable from at least 4 other people in the dataset based on certain key identifiers, makes finding you much harder.
These technical fixes sound pretty complex.
They are, and if we look bigger picture, even more recent theoretical models are emerging, like differential privacy.
Differential privacy. Okay, how does that work?
Imagine you ask a question about a huge database, like, what's the average age of patients with condition X? The system adds a tiny mathematically controlled amount of noise or randomness to the answer it gives back.
Okay.
Why? That noise cleverly ensures that even with the answer, you can't definitively tell if any single individual's information was included in that calculation or not. It protects individual privacy while still letting researchers get valuable aggregate insights.
Huh. That sounds incredibly powerful for balancing utility and privacy. But are there downsides? Does it always work perfectly, or does it, I don't know, make the results less accurate?
That's a great question. It offers strong mathematical guarantees of privacy, which is fantastic. But designing and implementing it effectively can be quite complex. And yes, there's sometimes a trade-off. You might sacrifice a tiny bit of precision in the aggregate results to gain that privacy. Making it truly practical and easy to use across the board is still an active area of research.
Got it. So, powerful idea. Still working out the kinks in practice. Okay, shifting gears a bit. What do everyday people, patients and the public, actually feel about sharing their health data for research?
Our sources from the Journal of Medical Ethics looked right at that. And generally, people express a strong willingness to share their data.
Really? Despite the privacy concerns?
Yes, primarily because they want to contribute to advancements in healthcare. There's hope for future personal health benefits, too, and even just pure altruism, especially among older citizens. They want to help the greater good.
That's encouraging. What benefits do they see?
They see significant potential. Better patient care through improved diagnosis and treatments, maybe more efficient use of healthcare resources, the ability to study long-term treatment effects or rare diseases, which you can only do with large populations. Some even believe it can spur innovation and cut down on waste in research.
But there's always a but.
Right. That willingness definitely decreases when people have higher privacy concerns or if they distrust government oversight, for example. Which brings us back to that critical point. How do you build and maintain trust, especially when breaches happen?
So who do people think should be responsible for managing this data sharing?
Ultimately, they tend to place the responsibility on researchers themselves. They suggest things like data access committees. These committees ideally would include maybe a researcher from the original project, a clinician, importantly, a patient representative, and maybe even a study participant.
So diverse perspectives making the decisions.
Exactly. And they also really value strong sanctions for data misuse. Accountability is key to trust.
Okay, so we've looked at the individual's perspective, the privacy paradox. Now let's pivot to the researchers themselves. You'd think with all this data flooding in, all this advanced tech we just talked about, labs would be humming along like well-oiled machines, right?
You would think so. But here's where it gets really interesting again. A study from the Journal of the American Medical Informatics Association paints a very different picture. It turns out that these rapid advances in analytical technology, combined with widespread access to large, complex biomedical data, have actually dramatically increased the difficulties researchers face.
Increased? How?
In acquiring the data, archiving it properly, annotating it so it makes sense later, and actually analyzing it. Investigators are finding data handling itself is a major barrier. The computational solutions they need are often way too expensive or too complex to implement, or sometimes they just don't exist yet for their specific dynamic needs, which can literally change week to week.
So given these huge data handling problems, how are these cutting-edge scientists actually managing day-to-day? Are they using super sophisticated custom tools?
Well, this is Here's the surprising part. The study found a widespread use of non-specialized applications for core data management.
Non-specialized? Like what?
Like general-purpose tools, spreadsheets, text files, simple file-sharing programs. We're talking Microsoft Excel,
Yeah,
basically.
kidding. Spreadsheets. For biomedical research data.
I'm not kidding. One researcher in the study literally said, quote, "Yeah, the spreadsheet has been our main workhorse, unfortunately." Another shared, quote, "I have one spreadsheet that has all of my chromosomes. It has all of my data. It has my whole experiment."
Wow. Wow. That's genuinely astonishing.
It really is. The startling takeaway is that despite all the cutting-edge science, a significant chunk of biomedical research is bottlenecked because scientists are managing like terabytes of complex data using Excel. It's like building a rocket with, I don't know, hand tools.
Okay, so they use them because they're simple and available, I guess. But what are the real downsides in a research context? They must know it's not ideal.
Oh, they know. 9 out of 15 researchers interviewed recognized the disadvantages loud and clear. Size constraints, for one. Spreadsheets just bog down or crash past a certain point, maybe 20,000 cells, the study mentioned. Limited processing power. They're cumbersome for printing or trying to link data between different files.
So they know these aren't the right tools, but they're stuck using them.
Pretty much. Out of necessity, it seems. And this reliance on ad hoc methods leads straight to another major problem. Just organizing, storing, and retrieving the data becomes a nightmare.
I can imagine.
Researchers are dealing with incredibly complex, varied data formats. The number of files and their sizes just keep growing, and indexing and annotating consistently, forget about it sometimes. Many just prefer their own individual, often informal methods. Some admitted to having no organizational methodology at all.
No organization at all. That sounds chaotic.
Picture this quote. They're not organized in any way. They're just thrown into files under different projects.
Oh, my goodness.
And you've got separate files on different computers that don't talk to each other, so finding something specific later, good luck. Many aren't even aware of basic search tools that might help.
This lack of organization, the wrong tools, it must kill productivity.
Absolutely. It has a direct, measurable impact. 41% of the survey respondents said data handling caused a backlog in their lab's productivity. Another 22% said somewhat.
So nearly 2/3 are feeling the pain.
Yep. And the problem was even worse. In larger labs, 51% reported a definite backlog. The fields most affected were structural biology, 62%, proteomics, 59%, and genomics, 50% fields generating massive data sets.
And what kind of data causes the most trouble?
Microarrays, those chips used to measure gene expression, and medical images were mentioned most often. Just the sheer size and complexity. And get this, over half of the researchers said they spend more than 5 person-hours per week just on data handling.
5 hours a week. That's like a significant chunk of someone's job just wrestling with files.
Exactly. It's essentially a full day of work lost per person, just managing data instead of analyzing it or doing experiments.
So if they're drowning in data and wasting time, what do they need? What are they asking for?
Well, they anticipate needing much better methods for managing these huge data sets, obviously, and better ways to actually process and analyze the data. They express a real need to move away from everyone doing their own thing, these individual preferences, towards established lab-wide data organization systems.
Like real database.
The truly searchable databases, yeah. Things that aren't hampered by crazy long file names or inconsistent updates or files scattered everywhere.
Okay, the need seems crystal clear. So what's stopping them? Why isn't this happening?
Right, that's the critical question. The study identified 3 main barriers. No huge surprises here, maybe. First, financial burden, money. 21% felt a specific software product could solve their urgent problems, but the cost is just prohibitive.
Software for labs can be expensive, right?
Very. One researcher put it bluntly. No, whenever I hear the word LIMS, that's Laboratory Information Management Systems, specialized software, I hear way too much money to deal with. Labs often underestimate these data handling costs when writing grant proposals, and there's a wariness about investing in new solutions, maybe because of past failures or just lack of experience with them.
Okay, cost is number one. What else?
Second, lack of time, just sheer time pressure. The time needed for proper data management, for training people on new technologies, it isn't always seen as an integral part of the research process itself.
It's seen as overhead, not research.
Kind of. Another researcher said it's free in terms of money. It's not free in terms of your time. This leads to what the study called incredibly time-wasteful methods on slow computers by untrained people.
Yeah.
And it's made worse by high employee turnover in labs. New people constantly have to learn these inefficient ad hoc systems from scratch.
Right, the training burden. Okay, cost, time. What's the third barrier?
Third, limited institutional support. More than half of the researchers felt that better support from their university or institution would help immensely. They believe universities, which get indirect costs or overhead from research grants, should provide more basic data infrastructure, things like shared storage, better networks, technical support. That could save individual labs much-needed funds.
So institutions could step up more. Okay, that's a pretty stark picture of the struggles researchers face just managing the data, let alone analyzing it. And speaking of analysis, let's pivot to a specific and incredibly fast-moving area, genomics. Historically, the big bottleneck in genomics was just the cost of sequencing the DNA itself, right?
Absolutely. It used to be tens of thousands of dollars for a single sample. Computational analysis, like a few bucks. Almost an afterthought in the budget.
But here's the fascinating pivot our sources point out.
Here.
Sequencing costs have just plummeted, nosedived.
Dramatically. We're talking full human genomes for around $600 now. Some companies are even reporting $100 genomes on the horizon.
Tens of thousands to maybe $100. That's insane.
It's a complete game changer. And if we connect this to the bigger picture, it means the computational cost and efficiency have suddenly become way more important. They're now a major factor, maybe even the major factor. The analytical pipelines, the software, are now struggling to keep up with the sheer volume of raw sequence data pouring out. We can't just rely on Moore's law making computers faster or Kreider's law making storage cheaper to automatically solve this. The data growth is outstripping those trends.
So what does this flip mean for researchers on the ground?
It means they don't just need to get compute resources anymore. Now they have to explicitly think about and trade off different factors. Accuracy versus speed, compute power versus storage cost versus the complexity of the infrastructure needed.
Trade-offs. Can you give an example?
Sure. Imagine a clinician analyzing a patient's genome for a rare disease. A full best practices analysis might take over 10 hours on a typical server. Or maybe it costs $5 on the cloud, but still takes tens of hours. But if they use specialized hardware acceleration, like something called Illumina Dragon, maybe it takes less than an hour, but it might cost $20 on Amazon Web Services for that speed.
Okay. So faster costs more. A time-money trade-off.
Exactly. And it's not just a technical decision anymore. It becomes part of the experimental design. How fast do I need this result? How much am I willing to pay for that speed? It's a resource allocation choice.
So what are the key trade-offs that developers making these tools and the researchers using them are constantly juggling?
Our sources break them down nicely into technical bottlenecks and then user-facing bottlenecks.
Okay, let's start with the technical ones.
All right. First, compute. It's not just about the theoretical speed of an algorithm, like how fast it scales. Just parsing these massive files, we're talking 50 to 100 gigabytes, compressed takes a significant amount of time. And analysis pipelines aren't just one step. They're often many small steps, and all those little compute times add up.
Right, it's death by 1,000 cuts, computationally speaking.
Kind of, yeah. Second, space, both storage and memory, RAM. Storage is an ongoing cost. It accumulates. Long-term archiving on magnetic tape might be super cheap, less than a cent per gigabyte. But shorter-term, faster storage on hard drives or SSDs costs more.
And then there's memory. The RAM needed to actively work on the data.
Exactly. RAM is often a hard constraint. If your analysis needs more RAM than the machine has, things grind to a halt or get incredibly slow. Cloud computing helps here, because you can spin up a high-RAM virtual machine just when you need it, which is much more flexible than buying physical hardware you might not need all the time.
Okay, compute, space. What else on the technical side?
Communication. Moving the data around.
Right.
This is often a more severe bottleneck than storage, surprisingly.
Moving data.
Yeah. Sending data out of the cloud, for instance, incurs egress costs. Google Cloud charges maybe 12 cents per gigabyte. It adds up fast with huge data sets. And these big cloud-based biobanks, like the UK Biobank or the NIH, all of us project, they keep the data in the cloud, which means researchers basically have to do their computation there in the cloud environment.
Which costs money and requires specific skills, right?
Exactly. It can cost millions for large projects, and you need platform-specific expertise. That limits who can easily access and analyze the data. It's a democratization issue. Another example, For single-cell sequencing, researchers might pre-compute a count matrix to reduce the amount of data they need to move. But doing that means you lose the raw information, which can sometimes skew the results. Another trade-off.
Okay, those are the technical trade-offs happening behind the scenes. What about the user-facing bottlenecks, the things a researcher actually experiences?
Right. These are more tangible. First, time. Simple question. How long do you actually wait for your results?
The turnaround time.
Precisely. Hardware accelerators, GPUs, FPGAs can slash compute time dramatically. But there are non-compute delays too, like waiting in a queue if you're sharing a high-performance computing cluster. Or just the time it takes to physically transmit terabytes of data or move it between fast and slow storage tiers.
And the time needed depends on the goal, too.
Totally. Research needs like running hundreds of samples in parallel over days or weeks are different from clinical needs, where you might need results for a single patient urgently, maybe in minutes, not hours.
Okay, time. What's next? We mentioned it before.
Money, the explicit time-money trade-off. Pay more for faster machines. Pay for priority access in the cloud queue. If you guess wrong about how much RAM you need, your job might crawl by swapping data to disk, or you might need to stop and request a bigger, more expensive machine. Again, the cloud offers flexibility here compared to buying fixed physical hardware, but that flexibility comes at a per-use cost.
Time, money, what else?
Accuracy. This one's subtle but absolutely critical. Modern methods, especially things like data sketching, sometimes intentionally reduce accuracy to gain speed or save memory.
Wait, they reduce accuracy on purpose? Isn't accuracy the whole point?
Well, it's about sufficient accuracy. Think of the classic BLAST tool for sequence alignment versus the older, slower Smith-Waterman algorithm. BLAST is way faster, but it's technically less sensitive, less accurate in finding all possible alignments. But for many tasks, it's good enough.
Ah, okay. Good enough is the key.
Right. It's about functional equivalence.
Yeah.
Does slightly reducing the precision of an intermediate calculation actually change the final biological conclusion you draw from the whole analysis? Some tools, like one called MASH for comparing genomes quickly, actually make you set parameters that directly control this accuracy speed trade-off.
So how do you know how much accuracy you can sacrifice?
It's tricky. A good rule of thumb might be you can reduce accuracy up to the point where the uncertainty it introduces is roughly similar to the uncertainty you'd get just by rerunning the original biological experiment.
Okay, that makes sense. Time, money, accuracy.
Yeah.
Is there one more user bottleneck?
Yes. Complexity. Just the sheer difficulty of developing, deploying, and using this high-performance software. Developers often have to use low-level languages like C++ for maximum speed. Then they might wrap that code or glue it together using easier languages like Python.
That sounds complicated.
It is, and sometimes that glue code itself can take a surprising amount of runtime, especially if you're dealing with messy or non-standardized file formats, which is common in new, rapidly evolving fields like single-cell analysis. Plus, just setting up and configuring high-performance bioinformatics software often requires specialized skills. It's not always plug and play.
So it's a challenging landscape with all these trade-offs. But are solutions emerging? Are things getting better?
Oh, definitely. There are some really clever approaches being developed to tackle these bottlenecks head-on.
Like?
Well, data compression is a big one. Classic compression saves storage space, but you often pay a penalty in compute time to decompress the data before you can use it. So now there's a push towards compressive genomics techniques that try to operate directly on the compressed data, like in standard formats called CRAM or BAM, avoiding that decompression overhead.
Operate on compressed data.
Cool. Yeah. And there's also lossy compression in genomics.
Lossy. Like JPEGs for images, where you lose some detail.
Exactly like that.
Yep.
Discarding information that might not be critical for downstream analysis, like maybe detailed quality scores for every single DNA base to achieve much higher compression ratios. Again, it's that accuracy trade-off, but applied to file size.
Interesting. What else?
Data sketching. This goes even further than lossy compression. Instead of just compressing, it extracts only the most important salient features from the data, creating a much smaller sketch.
Like a summary of the data.
Kind of. It allows for incredibly fast comparisons and analysis because you're working with the small sketch, not the massive original file. Examples include MASH, which we mentioned for estimating genomic similarity very quickly, or minimizer-based approaches, like the popular tool Minimap2, for rapidly mapping sequence reads. For single-cell analysis, there are even geometric sketching methods like GeoSketch and Hopper that can create representative sketches of cell populations, sometimes even improving the detection of rare cell types compared to analyzing all the data.
So sketching can actually improve results sometimes while being faster.
In certain cases, yeah, by focusing on the essential patterns. Then, of course, there are hardware accelerators.
GPUs and FPGAs.
Right. Graphics processing units and field programmable gate arrays. They're being used in commercial platforms like Illumina's Dragon or NVIDIA's Clara Parabricks to provide massive speedups for specific common bioinformatics workflows, like aligning sequences or calling variants. They require specific programming expertise and investment, but the speed gains can be enormous.
Okay, compression, sketching, hardware. But what about the cloud?
Cloud parallelization is huge. The cloud gives you on-demand access to a vast range of different server types, solving that problem of needing specific, expensive hardware locally. It also helps centralize data storage and compute for these massive biobanks we talked about, reducing overall costs and enabling huge reanalysis projects across thousands or millions of samples that would be practically impossible otherwise.
And finally, making the software itself easier to build.
Yes, that's the goal of domain-specific libraries and languages, trying to simplify bioinformatics software development. Libraries like BioPython or RustBio provide reusable building blocks for common computational biology tasks, and domain-specific languages like SnakeMake or the Galaxy platform make it much easier to define and run complex multi-step analysis workflows without writing tons of custom code. There are even newer programming languages being developed, like one called Sec, that aim to combine the ease of use of something like Python with the performance of compiled languages like C++. That's kind of the holy grail.
So lots of innovation happening to try and tame this data deluge and manage the trade-offs. It really feels like the world of biomedical data is, well, a classic double-edged sword.
It absolutely is. On one side, you have this immense, almost unbelievable promise for scientific discovery, for personalized medicine, all fueled by sequencing getting cheaper and cheaper.
But on the other side,
On the other, you have these profound challenges around privacy, the practicalities of data management we just discussed, and the very real and growing costs of computation.
and what's really striking from our discussion is how intertwined all these issues are, isn't it?
Completely. The need for faster analysis drives new tools, which create new trade-offs. Privacy concerns shape how and where data can even be shared or processed in the first place. It's this constant dynamic balancing act between getting the most utility from the data and ensuring adequate protection.
And as the amount of data keeps growing, the complexity increases, more of it gets generated in real time, maybe from your smartwatch, your fitness tracker.
Yeah,
The decisions about how we manage, analyze, and protect it are only going to become more critical.
And it's not just an issue for the experts in the lab or the cloud architects. These decisions directly impact what research actually gets done, what breakthroughs are possible, and ultimately what might be possible for your own health down the line.
This whole deep dive really makes me wonder. As our ability to generate and analyze more and more of our own biological data increases personally through consumer tests, wearables, whatever comes next, how much control do you, the listener, truly want over its use? And what trade-offs are you personally willing to make between your privacy and the potential benefits of scientific advancement for everyone? It's something to think about. That's it for this deep dive. Join us next time for another journey into the fascinating world of knowledge.
Sorry for that. Do I need the camera? Do I need my face on or not? Oh. So I had like eight viewers at some stage. And then now it's down to 7, whatever. I don't know, normally when I start talking, the views go down. Unfortunately, or fortunately, depends how you look at it. Depends how you look at it. So what was the other thing we were doing? Ooh, we have now 30 minutes. Should we do it at like 1.5 or something? So we essentially had these questions and answers that someone posted on LinkedIn. They're around data science, and we want to turn them, make them relevant to brainwaves, epilepsy stuff. Let's see if we give me a sec. We'll open it separately. Right. Yeah, I'll go over these questions. Says slideshow. Yeah, we have question 1. Yes, this is was contributed on LinkedIn by Ivan Reznikov. That's on LinkedIn. So go over the questions. We popped it into Gemini. So first of all, it seemed to be obviously able to answer all these questions 100%. Second, we asked, we had a prompt for this document. So essentially we're repeating each question and summarizing it, answering each question, providing the logic of the answer, explaining it to a layperson as well, importantly, so no terminology or as little terminology as possible. And then we give an example from biomedical data, specifically brainwave recordings in epilepsy patients. So how would you use this concept, for example, in this case, cross-validation, in detecting epilepsy seizures in brainwaves in EEG recordings from, well, epilepsy patients. And we gave it so we used Gemini 2.5 Pro for generating a response for this, going over the PDF. This PDF, there's quite a few questions, and then we gave it to Notebook LM. So just let it chat. If you have any questions, pop them in the chat, and I'll intervene. Or if it said something weird, which hopefully no. Gemini is now a BioniChaos CEO, so it better stay on topic at least.
Have you ever felt just swamped by all the technical jargon in data science? Or maybe wished for a faster way to, really get those complex ideas?
Well, you're in the right place today. We're taking a deep dive into some pretty fundamental data science concepts. Our source material is this really interesting set of data science mock test solutions, specifically focused on EEG applications. So this means we're not just looking at what these concepts are, but we're digging into the how and the why they're so critical, especially for real-world stuff like biomedical applications. We'll focus on how these ideas help us understand brain signals and even detect conditions like epilepsy.
Exactly. And the goal here really is to make these concepts feel immediately relevant. We want to highlight their practical impact, turning what might seem complex into clear insights for you.
Absolutely. Get ready for, hopefully, a few aha moments as we demystify these terms and show you their surprising real-world power. Okay, so let's start with building and training models. A term that always comes up is cross-validation. What's that really all about? Why is it so foundational? Right, cross-validation. It's a crucial technique. Its main job is to give you a realistic assessment of how well your model performs. And, maybe even more importantly, it helps reduce something called overfitting. The basic idea is you split your data set into multiple parts, they're often called folds. Then You repeatedly train the model on, say, most of the folds and test it on the one fold you left out. You keep doing this until every fold has been the test set once. This whole process gives you a much more reliable estimate of how the model will do on new data it hasn't encountered before.
So it's not just about getting a high score on the data you already have. It's about trust, right? Like, can you actually trust this model when it sees something new? Especially in medicine. You can't have a model that looks great on old patient data, but then completely misses something on a new patient. That's dangerous. It's like preparing a student for a big exam. You don't just give them one practice test they might memorize, right? You give them several different ones. That way, they really understand the material, not just the answers to that one test.
That's a perfect analogy, and applying it to the EEG example. Imagine building a model to spot seizures in brainwave recordings. You'd use cross-validation. Maybe split your EEG dataset into, let's say, 10 folds. You train the model on 9 of those folds, test it on the 10th. Repeat that 10 times, rotating which fold is the test set. Averaging the results from those 10 tests gives you a really solid measure of how accurately your model identifies seizures in new patient data. It stops the model from just specializing on the few patients in the initial training set.
Okay, so that prevents over-specializing. But what is that exactly? What happens when a model learns too well from its training data? You mentioned overfitting.
Yes, overfitting. That's exactly the problem. Cross-validation helps fight. Overfitting is when you see a big gap between how well the model performs on the data it was trained on versus how it performs on new, unseen data. Like maybe it gets 95% accuracy on the training set, seems amazing. But then you give it some new test data and the accuracy plummets to, say, 70%. That's a classic sign of overfitting. It means the model didn't really learn the underlying patterns. It just memorized the training examples, including all the noise and random quirks in that specific data, so it can't generalize.
Right, like the student analogy again. They memorized the practice exam perfectly, got an A+ WAR, but then the real exam had slightly different questions, and they tanked because they didn't actually learn the concepts. And in the medical world, if your seizure detector gets 95% on patient group A during training, but only 70% on new patient group B, that model basically just memorized the specific seizure patterns of group A. It didn't learn what seizures look like in general. That's overfitting.
Precisely. It failed to generalize, which is critical.
So how do we fix that? How do we actively prevent this over-memorization during training? There's a technique for that, right? Regularization.
That's exactly it. Regularization is a technique, or rather a set of techniques, designed specifically to combat overfitting. What it does, essentially, is add a penalty term to the model's learning process. This penalty discourages the model from assigning excessively large weights or parameters. It effectively forces the model to be simpler, to find more general patterns instead of fitting every little wiggle in the training data.
So it's like built-in discipline for the model. It tells it, hey, don't get too complex, focus on the big picture. Like telling that student, okay, you get points for the right answer, but you lose points for every overly complicated step you take. It pushes them towards the simplest, most general solution.
That's a really good way to think about it. When you're dealing with something like EEG data, which can have tons of features, high-dimensional data, it's super easy for a model to overfit. Regularization adds that penalty for large weights, pushing the model to rely on a broader set of features, each with maybe moderate importance, rather than just a few features with huge weights. This leads to better generalization on new patients.
Okay, shifting gears slightly, let's talk about the model setup. What are the things we actually set before training starts versus the things we measure after?
Right. The things you set before training are called hyperparameters. Think of them as the tuning knobs for the learning algorithm itself. For instance, with the random forest model, hyperparameters would be things like nestimators, how many decision trees you want in the forest, or max depth, how deep each tree is allowed to grow. You decide these before you hit train. Things like training accuracy, on the other hand, are performance metrics. They're results you measure after the model has been trained to see how well it did. Accuracy is an outcome, not a setting you choose beforehand.
Okay, got it. So like baking that cake again, hyperparameters are the recipe choices. Oven temp, baking time, how much sugar, you set those first. Training accuracy is like tasting the cake after it's baked to see how good it is. You can't just set the tastiness level in the recipe.
Exactly. So building our random forest for EEG classification, you might set the hyperparameters to use, say, 100 trees, each with a max depth of 20. After training, you might find the training accuracy is 99%. That 99% is a result, a metric, not one of the initial knobs you turned.
Makes sense. So once we've set those knobs, those hyperparameters, how does the model actually learn? How does it adjust itself to get better? There's a learning rate, right?
Yes, the learning rate is key, especially in optimization algorithms like gradient descent, which
Yeah.
many models use under the hood. The learning rate is another one of those hyperparameters. It controls how big of a step the model takes each time it adjusts its internal parameters to try and reduce its errors.
Okay, I think I need another analogy here.
Imagine you're blindfolded on a hillside, and your goal is to get to the lowest point, the bottom of the valley. You can feel the slope beneath your feet. You take steps downhill. The learning rate is the size of each step you take. Tiny steps mean you're cautious, you probably won't miss the bottom, but it'll take forever. Huge steps mean you get down faster, but you might completely overshoot the lowest point and end up halfway up the other side. Finding the right step size, the right learning rate, is crucial.
That paints a really clear picture. So for a neural network detecting seizures, the learning rate controls how much it changes its internal settings after seeing a batch of EEG data. Too high, it might never settle on a good solution. Too low, it might take ages to train.
Precisely. It governs the speed and stability of the learning process.
You mentioned internal parameters that the model adjusts. What exactly are those in something like a neural network?
Good question. In a neural network, the parameters are essentially the connection strengths between neurons, these are called weights, and the activation thresholds for neurons, these are called biases. Think of them as all the little internal knobs and dials that the network tunes during learning to transform the input data into the desired output prediction.
That sounds like potentially a lot of knobs and dials. Can you give us a sense of scale, like for a reasonably complex network?
Oh, it can get massive very quickly. Let's take a fairly standard, not even huge, network architecture, maybe something like 784, 128, 64, 10. That means 784 input features, 2 hidden layers with 128 and 64 neurons respectively, and 10 output neurons. Just calculating the weights and biases between layers. Input to first hidden, 784 inputs, 128 neurons, plus 128 biases equals 256 parameters. Second hidden output, 64 inputs, 10 neurons, plus 10 biases equals 650 parameters. Add those up. You're looking at 100,480 plus 8,256 plus 650 equals 109,386 parameters. Over 100,000 tunable knobs.
Wow. Okay, that's a lot. So if you feed a chunk of EEG data, maybe represented by 784 data points, into that network, it's adjusting over 100,000 parameters to learn how to tell if that chunk represents a seizure or not. That's incredible.
It really is. It highlights the complexity these models can capture.
So with all these connections and weights, what actually decides if an individual neuron in that network should pass on a signal? What's the trigger?
That's the job of the activation function. Each neuron applies an activation function to its weighted input to determine its output signal. Historically, functions like sigmoid or tan were common. They output values between 0 and 1, or midway 1 and 1, respectively. But these days, especially in the hidden layers of deep networks, the go-to activation function is ReLU, the rectified linear unit.
ReLU. Okay, what makes that one so special?
It's surprisingly simple. The function is just fx equals max 0x. So if the input x is negative, the output is 0. If the input is positive, the output is just x itself. This simplicity makes it computationally very fast. And, crucially, it helps mitigate a problem called the vanishing gradient, which used to make training very deep networks difficult. ReLU keeps the signal flowing better.
So it's basically like an on-off switch, but a bit smarter. Negative input means off, output 0. Positive input means on, and pass the signal through unchanged.
That's a great way to conceptualize it.
And for our EEG seizure detector, using ReLU in the hidden layers helps the network quickly pass along potentially important positive signals that might indicate seizure activity while just shutting down negative or irrelevant inputs. Efficient.
Precisely. It contributes significantly to the effectiveness of modern deep learning.
Okay, let's talk about the data itself for a moment. What happens when our data gets really, really complex? Like too many features or measurements for each sample?
That brings us to the infamous curse of dimensionality. It's a term that covers several problems that pop up when you're working with very high dimensional data. The main issue is that as you add more dimensions, your data points become increasingly sparse. They spread out exponentially. With a fixed number of data points, the average distance between them grows rapidly as dimensions increase. This makes it incredibly hard for algorithms to find meaningful patterns or clusters because everything looks far away from everything else.
Right, I think I can picture that. Like if you have 10 dots scattered on a 1-meter line, they might seem somewhat close. But put those same 10 dots inside a 1 by 1 meter square, they're instantly much farther apart on average. Then put them in a 1 by 1 by 1 meter cube. They become really isolated points floating in a vast space, harder to see any structure.
That's a perfect visualization. Now imagine EEG data. You might have, say, 256 electrodes on the scalp. And from each electrode, you extract maybe 10 different frequency band features. That's 256 times 10, 2,560 dimensions. If you only have recordings of a few hundred seizures, your seizure data points are incredibly sparse in that 2,560 dimensional space. It becomes really challenging for a model to learn what a typical seizure looks like because every example seems unique and isolated.
Okay, so that's the curse. If we have too many dimensions making our data sparse and patterns hard to find, how do we fix it? How can we simplify the data but keep the important stuff?
That's precisely where principal component analysis, or PCA, shines. PCA is a dimensionality reduction technique. Its goal is to transform your original set of potentially correlated variables into a new set of uncorrelated variables, called principal components. These components are ordered so that the first few capture most of the variance, or spread, in the original data.
So going back to that stretched oval cloud of data points, PCA finds the longest axis through that cloud. That's the first principal component. It captures the direction of most variation. Then it finds the next longest axis, perpendicular to the first, and so on. You can often describe most of the data structure using just the first few principal components, effectively reducing the number of dimensions you need to worry about.
Exactly. With high-dimensional EEG data from, say, 128 channels, the signals are often highly correlated. PCA can create new virtual channels, the principal components, which are combinations of the original channels. These components capture the dominant patterns of brain activity across the scalp. Often you can use just the first, say, 10 or 20 principal components as features for your seizure detection model. This drastically simplifies the problem, reducing dimensionality from 128 down to 10 or 20, while hopefully retaining most of the information critical for distinguishing seizures.
That makes sense. Related to having lots of features, can some features actually be redundant, like telling the model the same thing twice?
Yes, absolutely. That issue is called multicollinearity. It happens when two or more of your input features are highly linearly related, meaning they have a strong correlation. For example, if two features have a correlation coefficient of, say, 0.95, it means that when one feature's value goes up, the other feature's value almost always goes up by a predictable amount. They carry very similar information. This redundancy can make your predictive model unstable. The model might struggle to decide which of the two correlated features is truly important, leading to unreliable coefficient estimates and difficulty interpreting the model.
Like trying to predict, I don't know, a child's weight using both their height in feet and their height in meters. They're perfectly correlated, basically redundant information. Adding both doesn't help much and might just confuse things.
That's a perfect example. In an EEG context, imagine two electrodes placed very close together on the scalp. The electrical signals they pick up, and thus any features derived from them, like power in a certain frequency band, are likely to be extremely highly correlated. That's multicollinearity. In practice, you'd likely want to address this, maybe by removing one of the features or perhaps combining them into a single feature to build a more stable and interpretable model.
Okay, let's shift to how models make actual decisions or predictions. For something like logistic regression, it outputs a probability, right? A number between 0 and 1. How does that become a clear yes or no?
Right. Logistic regression gives you that probability. To turn it into a definite classification, a yes, class 1, or no, class 0, you need to apply a decision threshold. The most common default threshold is 0.5. So if the model outputs a probability of 0.5 or greater, you classify the instance as 1. If the probability is less than 0.5, you classify it as 0. Simple enough. So if the model spits out probabilities like 0.8, 0.3, 0.9, 0.1, using that 0.5 threshold turns it into 1010, it's like the weather forecast giving the chance of rain as a decimal. Your threshold is your personal decision point. Maybe you say, if it's 0.5 or higher, I'm taking my umbrella, that's class 1. If it's lower, I'll risk it, class 0.
That's a great way to put it. And the threshold itself can sometimes be adjusted depending on the specific problem and whether you care more about avoiding false positives or false negatives. But applying it to our EEG example, imagine an AI analyzing 1-second EEG segments. For 4 consecutive seconds, it outputs seizure probabilities, 0.8, 0.3, 0.9, 0.1. With a 0.5 threshold, a real-time monitoring system would flag the first and third seconds as potential seizure, 1, and the second and fourth as normal.
0. Makes sense. Now, logistic regression implies a kind of linear boundary. But what if the data isn't so easily separated? What if the yes cases and no cases are all mixed up in a complex way? That's a common scenario, and it's where support vector machines, or SVMs, really show their power, particularly with nonlinear kernels. A standard SVM with a linear kernel tries to find the best straight line, or flat plane, in higher dimensions to separate the classes. If your data points are tangled up in a way that no single line can cleanly divide them, the data is called non-linearly separable, and a linear SVM will perform poorly. The solution is to use a nonlinear kernel. Popular choices include the radial basis function, RBF kernel, or polynomial kernels. What these kernels cleverly do is implicitly map your data into a much higher dimensional space. The magic is that in this higher dimensional space, the classes might become linearly separable. So the SVM can then find a simple flat plane separator in that higher dimension, which corresponds to a complex nonlinear boundary back in your original feature space.
Whoa, okay. So imagine you have red and blue dots scattered on a dinner plate, totally mixed up. You can't draw one straight line to separate them. A nonlinear kernel is like, you hit the bottom of the plate really hard, the red dots fly up into the air, while the blue dots stay on the plate. Now, in this 3D space, plate surface plus height, it's easy. You can just slide a flat piece of cardboard horizontally between the blue dots on the plate and the red dots hovering above. That flat cardboard is your simple linear separator in 3D, but it corresponds to a complex boundary back on the 2D plate.
That is a fantastic analogy. It captures the essence perfectly. So if you're using an SVM to distinguish between, say, two different complex types of epileptic seizures based on EEG features, the decision boundary is probably not going to be a simple line. If your linear SVM isn't working well, trying an RBF kernel is usually the next logical step. It allows the SVM to learn that complex, wiggly boundary needed to separate the seizure types effectively.
Cool. Let's quickly revisit cross-validation. We talked about K-folds. Can you just spell out what that means in terms of the percentages used for training versus testing, like for 5-fold?
Sure thing. In K-fold cross-validation, you divide your data into K equal-sized chunks or folds. If you choose K5, you split the data into 5 folds. Each fold represents 15th or 20% of your data. In each round or iteration of the cross-validation, you use one of those folds, 20% of the data, as your test set, and you use the remaining K1 folds, in this case, 4 folds, which is 40 fixed or 80% of the data, as your training set. You repeat this process 5 times, making sure each fold gets its turn to be the test set.
Okay, crystal clear. So 5-fold always means an 80% training, 20% testing split in each iteration, like using 4 chapters of a 5-chapter book to study and testing yourself on the 5th chapter, then rotating which chapter is the test.
Precisely. If you had 1,000 EEG segments, 5-fold CV means 5 iterations. In each one, you train on 800 segments, 80%, and test on 200 segments, 20%. It's a very standard and robust way to evaluate model performance.
Speaking of performance, let's dive into evaluation metrics. We've trained our model. How do we know if it's actually any good? Let's start with the most basic one, accuracy.
Right. Accuracy is often the first metric people look at. It's defined simply as the proportion of total predictions that were correct. The formula is accuracy, number of true positives plus number of true negatives, total number of predictions. Let's use the example numbers from the source. Suppose a model made predictions and we found true positives, TP, 85 true negatives, TN, 120 false positives, FP, 15 false negatives, FN, 20. So the total number of correct predictions is TP plus TN equals 85 plus 120 equals 205. The total number of predictions made is TP plus TN plus FP plus FN equals about 85 plus 120 plus 15 plus 20 equals 240. Accuracy is then 205 divided by 240, which equals about 0.854. So roughly 85.4% accuracy.
Okay, so out of 240 predictions, they got 205, right? About 85% correct. Seems straightforward.
It is straightforward. So for an EEG model analyzing 240 segments, if it correctly flags 85 as seizures, TP, and correctly identifies 120 as normal, TN, its overall accuracy is 85.4%. It's right about 85% of the time.
But accuracy isn't always the whole story, right? What about models that predict a continuous value, like a quantity or a score, not just a yes-no class?
Exactly. For those regression models, accuracy doesn't really apply. A very common metric is mean squared error, or MSE. MSE calculates the average of the squared differences between the actual values and the predicted values. You square the errors so that larger errors are penalized more heavily, and also so that positive and negative errors don't cancel each other out. The key thing to remember is that lower MSE is better. It means the model's predictions are, on average, closer to the true values.
So if Model A has an MSE of 25 and Model B has an MSE of 16, Model B is the winner.
Correct. Model B is performing better because its average squared error is smaller.
It's like a golf score, then lower is better. And squaring the error really punishes those way off predictions. If you're predicting house prices, A model with lower MSE is generally making more accurate price estimates.
That's a good analogy. If you were building a model to predict, say, the expected duration of an epileptic seizure in seconds, and Model A had an MSE of 25, meaning the average squared error was 25 seconds squared, while Model B had an MSE of 16, you'd prefer Model B because its duration predictions are more accurate on average.
Is there another error metric for regression that's maybe a bit easier to interpret directly? Squaring things sometimes makes the units weird.
Yes, there is. I mean, absolute error, or MAU. Instead of squaring the differences between actual and predicted values, MAE just takes the absolute value of the differences and then averages them. So it measures the average magnitude of the errors in your predictions, regardless of their direction, over or under prediction. The units of MAE are the same as the units of your target variable, which makes it quite intuitive. Let's use the example. Actual values: 10, 15, 12, 8, 20. Predicted values: 9, 16, 11, 9, 18. The absolute errors are 10, 9, 1, 15, 16, 1. 12, 11, 1, 8, 9, 1, 20, 18, 2. The sum of these absolute errors is 1 plus 1 plus 1 plus 1 plus 2 equals 6. Since there are 5 data points, the MAE is the sum divided by 5. 6, 5 equals 1.2.
Okay. So an MAE of 1.2 literally means that, on average, the model's predictions were off by 1.2 units from the actual value. That is pretty intuitive.
Exactly. If a model predicts seizure severity on a scale of 1 to 25, and it has an MAE of 1.2, that tells clinicians that, on average, the model's severity prediction is likely to be within 1.2 points of the true severity. It gives a direct sense of the typical error margin.
Now, going back to classification metrics like accuracy, what happens if the data is really lopsided? Like you're trying to detect a very rare event, maybe 99% of the data is normal and only 1% is the event. Can accuracy be misleading then?
Oh, absolutely. Accuracy is notoriously misleading on highly imbalanced data sets. Think about it. If only 1% of your data is the positive class, like a rare disease or a seizure event, a lazy model could just predict negative for every single case. That model would achieve 99% accuracy. Sounds great, but it's completely useless because it never finds the rare event you actually care about. In these situations, you need metrics that focus on how well the model identifies the rare class. The F1 score is a much better choice here.
F1 score. Okay, what does that capture?
The F1 score is the harmonic mean of 2 other metrics: precision and recall. Precision asks, of all the times the model predicted positive, how often was it actually correct? Recall asks, of all the actual positive cases, how many did the model correctly identify? The F1 score combines these. To get a high F1 score, a model needs to have both high precision, not making too many false positive errors, and high recall, not missing too many actual positive cases. It balances the two.
Okay, that makes sense. Like being a detective looking for that one rare clue. Accuracy is bad because saying nothing here, 99% of the time, looks good but finds nothing. F1 score is better. It measures. Did you find the clue when it was there? Recall. And when you shouted, found it, was it actually the clue? Precision. You need both to be a good detective.
That's a perfect analogy. For EEG seizure detection, seizures are usually the rare positive class. Normal brain activity is the common negative class. A model just predicting normal all the time gets high accuracy, but zero recall, making it useless. The F1 score is preferred because it will only be high if the model successfully identifies most of the true seizures, high recall, without constantly raising false alarms during normal periods, high precision.
All right, let's move into some more advanced techniques. Can AI look at sequences of data, like EEG, over time, and actually predict future events?
Yes, that's the domain of time series forecasting, predicting future values based on past ordered observations. And for complex sequential data, like EEG, a type of neural network called LSTM, long short-term memory, is particularly well suited. LSTMs are a special kind of recurrent neural network, RNN, designed specifically to learn long-range dependencies in sequential data. They have internal memory cells that allow them to remember relevant information from much earlier in the sequence, which is crucial for many time series tasks. Other methods mentioned in the source, like k-means, which is for clustering, standard random forest, which doesn't inherently handle sequences well, or PCA for dimensionality reduction, are not designed for time series forecasting. LSTMs are really the tool for that job.
So predicting the stock market, or tomorrow's weather, those are time series problems. And LSTM acts like a forecaster who doesn't just look at yesterday, but remembers important patterns from last week, last month, maybe even last year to make a better prediction.
Exactly. And a really exciting application in the biomedical field is seizure forecasting from EEG data. The goal isn't just detection, but predicting that a seizure is likely to occur in the near future, maybe minutes in advance. This is fundamentally a time series forecasting problem, analyzing the sequence of EEG patterns over time. LSTM networks are one of the leading approaches being researched for this, trying to learn those subtle, time-dependent precursors to a seizure.
We touched on random forests earlier, which combine multiple models. What's the general idea behind combining models? Are there different strategies?
Right, combining models is called ensemble learning. The core idea is that a committee of models often performs better than any single individual model. There are two main strategies: bagging and boosting. Bagging, which stands for bootstrap aggregating, is what random forests use. The idea is to train many models, like decision trees, independently and in parallel. Each model is trained on a different random subset of the original data, drawn with replacement. The final prediction is typically made by averaging the predictions for regression or taking a majority vote for classification from all the individual models. Boosting, on the other hand, builds the models sequentially. Each new model tries to correct the errors made by the previous models. It focuses on the data points that were previously misclassified, giving them more weight. Examples include add-a-boost and gradient boosting machines, GBM.
Okay, let me try an analogy. Imagine a group of artists drawing a portrait. Bagging is like giving 10 artists slightly different photos of the person, random data subsets, and having them all draw their own portrait simultaneously. Then you digitally average all 10 portraits to get the final image. Boosting is more like one artist starts with a basic sketch. A second artist looks at it, identifies the biggest mistakes, and corrects them. Then a third artist looks at the corrected version, finds its biggest remaining mistakes, and fixes those. They work sequentially, each improving on the last.
That's a really excellent way to differentiate them. Captures the parallel versus sequential nature perfectly. So, in EEG seizure detection, a random forest, bagging, trains hundreds of decision trees concurrently on different bootstrap samples of EEG segments, and the final decision, seizure, or normal, comes from a majority vote. A boosting model might start with a simple classifier, find the EEG segments it got wrong, then train a second classifier focusing specifically on those difficult segments, and continue this process, building a strong final model sequentially.
So what's the big win? Why go through the trouble of building hundreds or thousands of models instead of just one? What's the advantage of these ensemble methods?
The primary advantage, almost universally observed, is better performance. Ensemble models typically achieve higher accuracy, better generalization, and more robustness compared to a single model. It boils down to the wisdom of the crowds. Individual models might have their own biases or make specific errors. By combining many diverse models, their individual errors tend to average out or cancel each other. This leads to a final prediction that is more stable, less prone to overfitting, and generally more accurate on unseen data.
Right. It's like asking one person a really tough trivia question, they might get it wrong. But if you poll 1,000 people and take the most common answer, you're much more likely to be correct. Ensembles apply that logic to AI models.
Precisely. A single decision tree trying to classify EEG might be very sensitive to noise or small variations in the data. But a random forest, an ensemble of hundreds of slightly different trees, is far more robust. An error made by one tree is likely outweighed by the correct votes of the majority, leading to a more reliable clinical tool.
Okay, one last concept, shifting gears a bit again. What if our data isn't nicely structured numbers from sensors, but say text, like doctor's notes or medical reports? How do we find the important information there? There's something called TF-IDF.
Yes, TF-IDF. It stands for Term Frequency, Inverse Document Frequency. It's a fundamental concept in natural language processing, NLP, and information retrieval, used to score the importance of a word within a document that's part of a larger collection or corpus. It has two components: term frequency, TF. This is simple. How often does a specific word appear in a particular document? More occurrences mean higher TF. Inverse document frequency, IDF. This measures how common or rare a word is across the entire collection of documents. Words that appear in many, many documents, like the, is, and, get a very low IDF score. Words that appear in only a few documents get a high IDF score. They are more discriminating.
So the TF-IDF score for a word in a document is high if that word appears frequently in that specific document, high TF-IDF, but is relatively rare across all the other documents, high IDF. Is that right?
Exactly. It finds words that are characteristic of a particular document.
So it helps a computer pinpoint the key terms. Like in a news article about politics, the word election might appear many times, high TF, and might be relatively rare across a huge corpus of general documents, high IDF, giving it a high TF-IDF score for that article. But a word like because would have a low IDF score everywhere.
That's a perfect illustration. And while TF-IDF originated in NLP for text documents, the underlying principle has relevance elsewhere too. Imagine you have thousands of neurologist reports associated with EEG recordings. You want to automatically identify all reports discussing a specific, rare type of seizure syndrome. You could use TF-IDF on the text of these reports. Medical terms specific to that rare syndrome would likely have a high term frequency within the relevant reports and a high inverse document frequency across the entire database of reports, since the syndrome is rare. This high TF-IDF score would make those terms powerful indicators for classifying or retrieving those specific reports.
Wow. Okay, we've really covered a lot of ground there. From the basics of checking model performance with cross-validation, to handling overfitting with regularization, understanding hyperparameters, diving into neural networks with real U and parameter counts, then tackling data issues like dimensionality with PCA, making decisions with logistic regression thresholds and SVM kernels, evaluating performance with accuracy, MAC, MAE, and the crucial F1 score for imbalanced data, all the way to advanced methods like LSTMs for forecasting and the power of ensemble methods like bagging and boosting, and even TF-IDF for finding key terms. That's quite a journey through data science concepts.
It really is. And what's truly fascinating, I think, is seeing how these ideas, which can seem quite mathematical or computational on the surface, translate so directly into powerful practical tools. You've seen their potential, especially in a field as critical as medicine, to significantly enhance how we understand complex biological signals like EEG, detect conditions, and maybe even predict them.
Yeah, it gives you real appreciation for the precision involved, the clever workarounds for challenges like the cursive dimensionality, and just the sheer ingenuity behind making these algorithms work effectively in the real world.
Which leads to a final thought, perhaps. We've seen how these algorithms can analyze incredibly complex data like EEG to detect current states, like seizures. But given their power to learn intricate patterns, especially sequential ones with things like LSTMs,
But
how might these advancements move beyond just detection? Could they learn to genuinely predict, or maybe even guide interventions to prevent neurological events in ways we're only just starting to scratch the surface of? Something for you to think about.
Yeah, feels like I'm going to do a very long lecture. That's okay. You know, what's the retention? What do you think the retention is like out of Notebook LM summary? Well, we requested it, so it's meant to be relevant. Yeah, it's good that you can just pop this this exam sheet, and then just add examples that will be more relevant to you from whatever your field. Should we test our retention straight away? Probably not. I think I heard some supposedly evidence that you shouldn't be, doing a retention test straight after the lecture. So I might do it at another time. We might be actually deploying a lot of these things as interactive web applications, so that will help us understand these concepts even further.
We're making powerful biomedical tools accessible to everyone.
Ever wondered what your brainwaves sound like? Or look like? Ever wanted to play with real scientific tools? Ours are free and open source. You won't believe what you can do with your own data.
Want to dive into data science? Start with our interactive tools.
Go ahead. Play with the data. Everything we do is available freely on BioniChaos.com. Please consider supporting me on Patreon, and don't forget to click like, subscribe, and comment.
There is a human in the loop, obviously, so if you have any questions, pop them in the chat. I probably won't be able to answer them myself anyway, so I'll have to give them to one of the models available to us. We have Gemini standalone, and we also pretty much have all the other major models through GitHub Copilot. Through GitHub Copilot. You could actually develop on the site. Could actually develop on the site, but it had to be logged in or something. Yeah, we actually have some repositories. So that one, you can add a GitHub repository to it and just code within the browser. Yeah, we have some of them currently set in private. I mean, you can see all the code on the website. Anyhow, so the code should be on BioniChaos.com. Yeah, I'm just thinking, should we at some stage teach Visual Studio Code? Because currently we're still using Visual Studio Code. Well, I mean, it works. And you have the chat. We have a few new tools that are coming up. We have a few tools that are coming up. I was thinking, should I comment on this? Like someone was saying, stop your bot. I don't particularly, I think people on LinkedIn do not like AI for that reason. Well, first of all, I'm not letting it run by itself. Well, actually I do. So we do run it as an agent. So this is essentially the whole code base for BioniChaos website. Everything is now Java, so we're trying to primarily do JavaScript. So most of it will be visible for you. So essentially the source code will be on the website itself. So Yeah, we haven't deployed in a while, so we're deploying from here, well, which we can just do from a text file. So we have all the prompts for deploying, modifying, adding tools. So essentially I'm using Visual Studio Code to make the web application ready for production. And in here we have, so first of all, you can select your ask, agent, or edit. Once you actually, interestingly enough, that you can switch between ask and agent. So here I was like talking to it with 4.1, but then I can talk to it with reasoning models as well. GitHub Copilot just introduced those caps on. Don't quite understand how they work. Or one is taking up a whopping 10 times rate. So essentially you have like a monthly quota, a monthly rate, and O1, ChatGPT O1 is taking 10 times any other model. Like, I mean, Gemini takes one, so that's surely Gemini 2.5 Pro are they suggesting that O1 in preview as well, meaning, the deployment, the integration is beta, but that is suggesting it's like 10 times better than Gemini 2.5 Pro. I don't think so. Yeah, 4.0 and 4.1 are included. Well, I guess that's because of the relationship between Microsoft and OpenAI. Yeah, we're not going into those. Not going into company politics and things like that. Just what's relevant is that they keep changing the rules every other day. So when you ask a question, you can actually go into agent mode. It will start chipping away, hopefully based on the previous discussion, because when you go into edit mode, it's actually asking you to start a new edit with Copilot session. There used to be separate tabs. There used to be two tabs, ask and edit. Now there are agents in the mix, and yes, those agents are quite powerful. They can add files, execute stuff. Normally before executing or adding files, it will actually ask you, to confirm. So yeah. So if you check the website already, do let me know. So essentially, if you hit F12, you should see all the source code for each one of those applications. So it will be mostly in a single HTML file. So those will be very long files because, more than 1,000 lines for this web application. Well, because all the JavaScript code, essentially all the code is within the HTML. So you can just grab it, run it on your website, do whatever you wish. We have a open source, open access, free access, freedom, whatever, to education policy on BioniChaos.com, so you can go and use the code. Yeah, this one, for example, we tested quite a bit. If you want to participate in testing, go ahead. Yeah, you can go ahead and test the web applications yourself, either on the site or just grab the code, run it wherever else you like. So this is, yes, in the past we used to have some Flask applications. So they have a backend, but essentially one of the processes that we're going through is taking those older Flask applications and turning them into standalone HTML front end only. So, well, first of all, so I don't run anything on my server, so I don't waste unnecessary electricity. So my electricity bills are reduced, and also that you have access to the code straight away. I was saying in the past that, in this stream, so we're live streaming all the process of all the development on YouTube. As you can tell if you are watching this. And in the past I was saying, currently this stream had up to 8 viewers. Now it's dropped to 5. And interesting enough, I'm essentially testing if when I start talking or showing my face, well, filtered, but still can reduce the filter a bit. Edge threshold, you can do a very high. This edge threshold of 11. Can do around 50%. Seems legit enough. If you're going all the way to 100, you can still see my hand, but not much else. Anyway, so these tools. The other thing, I'm not sure how useful it is. So I was deploying those this audio. This is again NotebookLM. Essentially, I've been giving the code of this web application to NotebookLM. In this case, it made 11-minute summary of the code. Yes, there's text at the bottom explaining what the web application all about. Trying to keep it consistent for all the other web applications, except that those 11-minute MP3 files can actually add up quite quickly. So I already have tens of them, and each one will be 40-50 megabytes. And so you would think that I could handle serving the audio summaries myself, but I might just keep them in the YouTube video. Well, because in the YouTube video you hear the audio.
Our goal really is to unravel how this brilliant tool takes a concept that can feel academic and makes it real. It lets you visually grasp.
Again.
Exactly.
Yeah, so that's NotebookLM. I might actually stop hosting them on the site, so they will be just available on YouTube, because on YouTube you would see me interacting with the tool. We also have auto demo now, which you can turn off and interact with the tool yourself. In general, when the auto demo is on, you should be able to take over. Instead of stopping demo, you should be able to just press any button and it will stop the demo for you. The robot that developed it didn't think of it. And surely it's not the original concept. So we covered this one quite a bit before. If you have any questions, do let me know. We covered the spectrogram as well.
Welcome back to the deep dive. We're here to unpack complex topics and really give you those insightful nuggets of knowledge. Today, we're diving into a field that honestly can feel pretty chaotic, biomedical data. But we're not just talking about the chaos. We're looking at a really interesting project aiming to bring some order to it all, making, super complex biomedical data simple and accessible for basically everyone. And to do this, we've gathered info from all over the project's website, academic papers, YouTube videos, even Reddit discussions. We're going to distill it all for you.
Exactly. Our mission really is to unpack how this specific project, it's called BioniChaos, is trying to democratize biomedical data processing. We'll look at some of its innovative tools, and then connect that to the bigger picture, things like medical education and some pretty deep ethical questions around advanced neurotechnology. By the end, you'll have a really clear picture of what's happening in this really vital and fast-moving field.
Okay, let's jump right in then. BioniChaos. Tackling this chaotic world of biomedical data, making it simple, accessible. How exactly does it do that? How does it break down those barriers? So like anyone can engage with EEG, ECG data, maybe stuff from wearables, just on a laptop or phone.
Yeah, what's really key here is the gap it bridges. Historically, getting your hands on this kind of data, processing it, that meant specialized knowledge, expensive software, powerful computers. BioniChaos wants to democratize that whole process. Accessible, open source tools, educational resources. It's built on values like accessibility, innovation, collaboration, education, and the fact that everything's under a Creative Commons attribution license that really says something and encourages people to use it, build on it.
And accessible really means accessible here. The tech side is, well, pretty clever. It's a self-contained platform. The code, mostly JavaScript, runs right in your web browser, which means, like you said, no downloads, no installs needed for the examples. It's all web-based. Responsive for mobile, too, though they do say it's best on a desktop. And importantly, they use de-identified public raw data, and they cite their sources for each tool. That feels like a big step for transparency.
Absolutely. And that accessibility opens the door to, well, a really diverse crowd. Researchers, students, sure, but also tech enthusiasts, healthcare folks interested in data science, BCIs, brain-computer interfaces, AI. The name itself, BioniChaos, kind of captures it, doesn't it? That sometimes chaotic result of combining biology and electronics. It actually started as a personal project, a biomedical engineer and scientist just wanting to get these tools out there more widely.
So what kind of processing are we talking about? What can you actually do with it?
It covers quite a range. Basic stats, naturally, but also more advanced stuff, like fuzzy logic that helps computers handle uncertainty, neural nets mimicking brain learning patterns, spectrograms, visualizing frequency changes over time, even image processing and classification. And the site has loads of practical examples, tools to understand signal features, predict events in the data.
Okay, practical tools.
But two really important caveats here. Need to stress these. First, it's experimental. It's not certified for clinical use, definitely not for diagnosis. It's provided as is.
Right. Good to know.
Second, and this is quite significant, absolutely no military use. The content, the tools, the resources, strictly off limits for military purposes. Their mission is clearly peaceful educational innovation.
Okay, non-military, non-clinical. Got it. Let's get into some of the tools then, the interactive applications. This sounds like where the learning really happens. The Lycidas curves visualization, you mentioned that one. Sounds intriguing.
Oh yeah, it's visually very engaging. Lets you explore the relationship between two oscillating signals, like two waves. You can tweak parameters A and B for frequencies, delta for the phase shift, and you see the curves change shape instantly.
So you can actually see the interaction.
Exactly. Like the example they give, a 1-to-5 frequency ratio. You literally see 5 vertical loops for every 1 horizontal loop.
Yeah.
It's quite mesmerizing. Yeah.
Cool. So it's educational, but does it have practical uses?
Definitely, especially in EEG analysis. It gives you a visual way to check for symmetry between the brain hemispheres.
Ah, okay. So differences might signal something.
Precisely. Neurological abnormalities or just functional variations, maybe how the brain responds during certain tasks. And think about real-time monitoring, like during neurosurgery or in an ICU. You could potentially spot sudden changes in brain activity much faster.
Wow, okay. Real-time feedback.
Yeah. And it's useful in cognitive studies, too, comparing hemisphere activity, potentially even as a diagnostic aid for things like epilepsy prediction or stroke detection.
Fascinating. What about the synthetic EEG signal generator? Why generate fake EEG?
Good question. It's actually incredibly useful. This web tool lets you create artificial EEG signals. Think about it. You can test algorithms, new devices, even theories without needing actual patient data initially, which can be hard to get and has privacy issues.
Right, a safe testing ground.
Exactly. You adjust things like amplitude, bandwidth, window size, and you see the signal and its power spectrum visualized right there. So great for R&D, validating your processing methods, and of course for teaching and training.
Okay, and I read something interesting. It generates random frequencies within bands.
Yes, that's a clever touch.
Yeah.
It simulates the natural variability you find in real EEG signals. Makes the synthetic data more realistic for testing.
And this connects to AI and machine learning, right? BioniChaos seems to use AI quite a bit.
It does, in a couple of ways. First, AI tools like ChatGPT and GitHub Copilot were apparently used in developing the site writing code, generating text content.
Okay, behind the scenes.
Right. But also, some of the tools themselves use AI for analysis. Things built with TensorFlow or PyTorch, those big AI frameworks. The sources mentioned examples like AI-powered EEG speech decoding, and discussions about how AI and machine learning are changing EEG and ECG analysis. They even touch on the challenge of AI understanding why causality in large language models like ChatGPT.
So AI building AI tools and AI within the tools.
Exactly. And there's this great quote from the BioniChaos creator on Reddit, something like, "Great products aren't built on clever code, they're built on clean, reliable, boring data." I think that really nails a key insight in this field.
That's a good one. Clean data is king. What about the cochlear implant simulator? That sounds very specific.
It is. It's a visualization tool showing how sound gets processed into electrical signals for the implant. And crucially, it simulates the physical insertion of the electrode array into the cochlea.
You can interact with that part.
Yeah, you can adjust parameters like insertion depth, the force being applied, the speed. All things that are critical in real surgery to avoid damaging delicate tissues.
Wow, and I saw something about robot-assisted insertion in the simulation.
That's right. The simulation allows for both manual, human-controlled insertion and robot-assisted insertion, which is interesting because currently it's mostly done by surgeons manually, so it's kind of looking ahead.
It really highlights how sophisticated this tech is getting, and the ethical side you mentioned earlier starts to loom larger.
Definitely. And these are just a few examples. The site has a whole suite of tools. Other signal generators, ECG, synthetic noise, lots of analysis tools, ECG feature extraction, EEG cross-coherence, fuzzy logic analysis for EEG, a 3D MRI viewer, gait analysis, something called myoscope for EMG muscle signals.
A lot to explore.
Yeah, and educational stuff too. Interactive brain EEG sims, Fourier series visualizations, a guide to EEG tech, even a hearing test, plus those games you mentioned, CardioBot for spotting weird ECG patterns, and the Mastering the ECG game, which apparently gets crazy fast.
Okay, so ECG practice that gets intense.
Seems like it.
You know, the fact that BioniChaos includes these games, it feels like it taps into that bigger trend we hear about. Game-based learning, GBL, especially in medicine. How big a deal is this GBL approach becoming?
Oh, it's definitely a significant trend. GBL is basically about using game elements in non-game contexts to boost engagement and learning. You've got sort of two main flavors. Serious games. These are actual interactive applications, often simulations, with goals, scoring, designed to teach specific skills or knowledge.
Right, like flight simulators, but for medicine.
Kind of, yeah. And then there's gamification, which is more about applying game mechanics, points, badges, leaderboards to existing learning activities to make them more motivating.
Yeah.
Layering game goals on learning goals.
Oh, and does it actually work in medical education? What are the benefits?
The research suggests, yes, it often does. The documented benefits are pretty compelling. Things like better collaboration among students, definitely higher engagement and motivation, which is huge, improvements in clinical reasoning, decision-making skills, even overall academic performance in some cases. And it provides a safe space for what's called deliberate practice, trying things, making mistakes without real-world consequences.
Can you give some examples?
Sure. The has mentioned quite a few. Cleft Island and Emerge for surgical training, Pediatric Sim and Neo Games for pediatric care and neonatal resuscitation. These
Yeah, I'm not sure if it's clear, but those, the ones that was just mentioned, they are not on BioniChaos.com. They are elsewhere. So this is what's available in the public, not on BioniChaos.com.
showed better long-term knowledge retention too. There was Antibigame Array for learning antibiotic use. Apparently 96% of students liked it. A COVID game helped improve knowledge during the pandemic.
Even board games.
Yeah. Gridlocked a board game about managing patient flow in the emergency department, and Happy Families, a card game for physiotherapy clinical reasoning. Even for continuing medical education, CME, there are spaced education games making that traditionally, let's be honest, sometimes tedious process more engaging.
Yeah, I can see how that would be more appealing. And during the pandemic, this must have been invaluable for remote learning, right? Keeping students engaged from afar.
Absolutely critical. When in-person clinicals and classes were disrupted, GBL offered a way to maintain interactive learning and engagement despite social distancing. It really surged in relevance then.
But it's not perfect, right? What are the downsides or challenges?
No, definitely not a silver bullet. There are limitations. Some studies, surprisingly, don't show significant short-term gains or even improved long-term retention compared to traditional methods.
Oh, interesting.
Yeah, and there's something called the expertise reversal effect. A game that works well for experts might actually confuse or hinder novices. Design matters hugely.
Makes sense. What else?
Well, cost and efficiency. Developing really good educational software, a polished, serious game, that can cost thousands, tens of thousands of dollars. You also need instructor training to use these tools effectively, plus ongoing technical support.
Resources, basically.
Right. And maybe the biggest challenge is evaluation. There isn't really a standard way to measure the specific impact of GBL. Lots of studies look at engagement, satisfaction, maybe simple knowledge recall tests, but they often miss higher-level outcomes. Does it actually change how doctors practice? Does it have a profound, lasting influence?
Deeper impact measurement is tricky.
Very. Plus, a lot of the studies have small sample sizes. We really need more large-scale multi-center research to get a clearer picture of its true effectiveness across different contexts.
Okay, so promising, but needs careful implementation and more research. Circling back to things like that cochlear implant simulator and the potential neuroenhancements you mentioned earlier, it forces us to confront some really big ethical questions. When we talk about neural implants devices in or on the brain for therapy, like Parkinson's, epilepsy, OCD, what are the main ethical hotspots we need to think about?
It's a minefield, ethically speaking. A huge one is this line between therapy versus enhancement. Cochlear implants seem clearly therapeutic, right? Restoring hearing, same for deep brain stimulation, DBS for Parkinson's.
Yeah, restoring function.
But then you have companies, like Neuralink is often discussed, exploring implants potentially for cognitive or sensory enhancement in healthy people. That blurs the line dramatically, raises huge questions about fairness, societal impact. What does it even mean to be normal or human if some people have augmented abilities?
A slippery slope argument almost.
Well, it's a serious concern. One study specifically looked at adaptive DBS, which adjusts stimulation automatically, and raised flags about using it for enhancement safety, naturalness, justice concerns. They basically said we need to understand the brain much better first.
Okay, therapy versus enhancement. What else?
Privacy and data security. This is massive. These devices could collect and transmit incredibly sensitive brain data, personal health information.
Like thoughts, literally.
Potentially, yes. While major breaches in current things like cochlear implants aren't widely reported, the industry knows cybersecurity is paramount. Protecting that data is critical.
And there's consent, right? Especially if the person can't fully consent.
Exactly. Consent and autonomy. Ensuring truly informed consent is a challenge, especially when the long-term effects might not be fully understood. Think about children getting cochlear implants. Parents decide. But does that predetermine the child's identity, their connection to deaf culture versus the hearing world? It highlights the need for ongoing conversations as the child grows.
Difficult choices.
Very. And linked to that is equity and access. These are advanced, likely expensive technologies. Is there a risk they'll only be available to the rich, widening the gap between haves and have-nots? The cost of the device, surgery, follow-up, maintenance, it creates huge barriers, particularly in lower-income settings.
So potential for inequality.
Definitely.
Yeah.
And then there's a more philosophical angle. Identity and personality changes. Could these implants fundamentally alter someone's sense of self? We see this debated with cochlear implants. Recipients sometimes navigate a complex identity between deaf and hearing communities. Altering sensory input can profoundly impact self-perception.
How you experience the world changes who you feel you are.
It can, yeah, through the complex interaction. And finally, dependency and device removal. What if someone becomes reliant on the device? What are the ethics around removal, especially if it's needed due to malfunction or infection?
Is removal common?
For cochlear implants, it's actually rare. A study looking at data from 1989 to 2021 found a pooled removal rate of about 4.7%, mostly for device failure or infection. The implants themselves are very reliable, high 5 and 10-year survival rates, like 95% and 94%. But the possibility of removal and the dependency aspect still raise ethical points.
Okay, so therapy versus enhancement, privacy, consent, equity, identity, dependency. Quite a list.
It really covers a lot of ground, touching on medicine, technology, society, philosophy.
So wrapping this up, we've gone from trying to make sense of biomedical data chaos with open source tools like BioniChaos, looked at how game-based learning is shaking up medical training, and then touched on these really profound ethical dimensions of neurotech. It feels like these fields are not just evolving separately, they're really starting to merge and interact in complex ways.
I think that's exactly right. And projects like BioniChaos, they're more than just code and data points. They're about empowerment, empowering individuals, researchers, students, you listening, to understand this stuff better, fostering a more informed, more collaborative future in biomedical science by making knowledge accessible.
It leaves us with a final thought, maybe. Perhaps the real chaos isn't just in the complex data itself. Maybe it's in how we, as a society, navigate the ethical maze that comes with these incredibly powerful, rapidly advancing technologies. So, thinking about everything we've discussed, what stands out most to you? How can you play a part, even just in understanding, and bringing some order to this fascinating chaos as these fields keep pushing forward?
Well, there's a human in the loop. If you have any questions, use the chat. Yeah, it's good. We actually it's nice that we actually know that people are listening, because once the bots stop talking, their views start dropping. I'm not sure the same thing kind of is happening when I start talking as well. So so go figure. Go figure. And let me know if you need my webcam on. Happy to turn that on. Otherwise, we'll save some energy. Yeah, obviously in this case, the bot AI is winning the human. Well, because the human wasn't paying attention, as per usual. Can we recover and get back to into the game? I don't think so. I think it's too late. The bot is winning by miles. Interestingly enough, with this noise level that this signal has, the bot is also making some mistakes. So it made 9 misses and 3 false alarms. That's quite interesting, isn't it? That's fuzzy means that it's the algorithm. The AI is actually deterministic, and it's using fuzzy logic. So it's actually looking at the thresholds for different segments, amplitudes at different parts of the signal to determine if it's normal or abnormal ECG waveform. Anyway, if there's a human who wants to interact. If not, we'll go back talking to robots.
Welcome to the deep dive. Today we're going to maybe challenge one of our most fundamental assumptions about health and even about cutting-edge medical tech.
Oh, how so?
Well, what if true health isn't about perfect, unwavering order?
Okay.
What if it actually relies on a precise balance that includes, chaos?
Chaos.
Right.
That definitely sounds counterintuitive.
It does, doesn't it?
Absolutely. I think when most people hear chaos, they think randomness, dysfunction, maybe something breaking down.
Exactly.
But in the world we're talking about today, the world of biology and these dynamic systems, chaos actually takes on this surprisingly rich and often really beneficial meaning.
That's such a crucial distinction to make right up front, and that really is our mission in this deep dive. We want to unpack the surprising, often essential role of what scientists call nonlinear dynamics and this idea of chaos.
Yeah, in our most fundamental biological rhythms.
Everything from your heartbeat, literally, to your brain activity. And then we'll get into how these complex principles are inspiring powerful new algorithms, tools for medical diagnosis, for prediction.
So the idea is, by the end of this, you'll have a kind of shortcut to understanding why chaos, in this biological sense, is often a very, very good thing for you, for health.
Mine to set it better.
Yeah.
And to guide us through this pretty intricate landscape, we've gathered some fascinating sources.
Yeah, we're drawing quite a bit from a foundational review article. It's all about chaos and order, specifically in biomedical rhythms.
And then we'll layer on top of that insights from 2 systematic reviews.
Right. One digs into the evidence for chaos and EEG signals,
Yeah.
brainwaves related to human performance. And the other explores these advanced optimization algorithms, techniques that are genuinely changing the game in medical diagnostics, using chaos-inspired ideas.
Okay, so let's start at square one. When we talk about chaos, biologically speaking, what are we actually getting at?
Well, nature fundamentally is just full of nonlinearities.
Non-linearities, okay. Sounds a bit technical.
It does, but think of it like this. In a simple linear system, right? You push a swing twice as hard, it goes twice as high. Predictable.
Makes sense.
But in a nonlinear system, which is most of biology, a tiny nudge might send it soaring unexpectedly. Or a huge push might do almost nothing.
Ah, okay. Unpredictable responses.
Exactly. It's this sort of unpredictable yet still rule-governed responsiveness that gives rise to the incredible variety we see in nature. And physiological rhythms like your breathing, your heartbeat, they're central to life.
And these rhythms can be.
They can be either periodic, nice and orderly, or maybe surprisingly irregular, chaotic even, over time and space.
That distinction feels really important. So extreme irregularity, sure, that can be a problem, but it's not always bad when things aren't perfectly predictable.
That's exactly right. Yeah. I mean, yes, abnormal rhythms can definitely arise from alterations in physiological control systems that leads to what some people call dynamical disease.
Dynamical diseases, okay.
But here's the kicker. Chaotic behavior isn't just random noise. It's actually seen as a typical response, often a healthy response of biological systems.
Really? A typical response?
Yeah, there's a great quote from the Nobel laureate Ilya Prigogine. He says something like, "Our physical world is a world of instabilities and fluctuations which are ultimately responsible for the amazing variety and richness of forms and structures we see in nature around us."
Wow, I love that. That totally reframes chaos. It's not something to just avoid. It's fundamental to life's richness, its adaptability.
Precisely.
So what are the key characteristics then? What defines this essential biological chaos?
Well, the most famous one, the one you've probably heard of, is sensitive dependence on initial conditions.
The butterfly effect.
That's the one, the butterfly effect. It just means that tiny, tiny differences in the starting point of a system can lead to wildly different outcomes down the road, over time.
Like the classic, a butterfly flaps its wings in China might cause a hurricane in Brazil. That came from meteorology, right? Lorenz.
Exactly, Lorenz's weather studies. But what's fascinating is the mathematician Henri Poincaré. He had an incredibly clear grasp of this way back in the late 19th century.
Really? Before Lorenz?
Yeah, studying complex celestial mechanics, he saw that even if you know the laws perfectly, tiny initial differences could still lead to vastly different, unpredictable outcomes.
So it's not just about weather or randomness.
No, it's fundamental. It shows how living systems can stay nimble. Those tiny shifts allow for a healthy range of responses, keeping the system adaptable, ready for anything.
Okay, so it follows rules, it's deterministic, but you still can't predict the long-term outcome perfectly. What else defines it?
Another key feature is the idea of fractals and strange attractors.
Fractals, like those cool patterns.
Yeah, exactly. Imagine a coastline, right? If you zoom in, it still looks just as jagged and complex. Little bays, little peninsulas, mirroring the bigger shape.
Self-similarity?
That's it. That's a fractal, a pattern that repeats at different scales. And they have this weird property, a fractional or non-integer dimension. And we see them everywhere in nature. The patterns in a fern leaf, the way smoke curls. And in chaotic systems, these patterns trace out what we call strange attractors.
Strange attractors, what are those?
They're like, think of it as the system's preferred range of behavior. It's a conceptual map. The system always explores within this complex fractal shape, but it never repeats the exact same path twice.
Ensuring constant variation. Adaptability again.
Exactly. It's this beautiful, complex, self-similar geometry that's a hallmark of these dynamic, chaotic systems.
So how do scientists actually study this in us, in the human body?
Well, there are two main ways. One is mathematical modeling, building realistic simulations.
Okay.
The other, maybe more common in biomedicine, is time series analysis. That means analyzing actual data, signals recorded over time.
Like from an ECG or EEG?
Precisely. But the challenge is real biomedical signals, things like your white blood cell counts over time, your heart rate variability, blood pressure, even something like a Parkinsonian tremor. They are incredibly complex.
Yeah, they jump around a lot.
Right. The source material calls them inhomogeneous and non-stationary. They fluctuate in this irregular, complex way. And it's that very complexity that makes time series analysis so useful for finding these hidden chaotic dynamics.
It makes total sense. Okay, so let's dive into some actual examples. Where does this chaos show up in the body? Let's maybe start beyond the brain for now.
Okay, a prime example is the cardiovascular system. Heart rhythms are a powerful demonstration of these dynamics in action.
How so?
Take heart rate variability, or HRV. It's not just about how fast your heart beats, but how the timing between beats varies.
Right, I've heard of HRV.
And it's a critical predictor. Low HRV can indicate risk for arrhythmic events, even sudden death after a heart attack. But here's the twist. Normal, healthy heart function often involves these subtle, complex, even chaotic variations in rhythm.
See, that's the counterintuitive part again. We tend to think a steady, regular heartbeat is the picture of health.
I know, it feels wrong, doesn't it?
Yeah. So how do we reconcile that? This idea that some irregularity, some chaos is actually good for the heart?
It's a great question. Think of it this way. A healthy heart isn't a metronome ticking perfectly.
Yeah.
It needs to constantly adapt to everything your body does. Standing up, breathing, stress, relaxation.
Okay.
And that adaptability expresses itself as variability. Sometimes complex variability that looks like chaos, it's a sign of responsiveness.
So rigidity is bad, flexibility, even if it looks chaotic, is good.
To a point, yes. And what's more, certain actual cardiac arrhythmias, things like premature beats, atrial fibrillation, even dangerous ventricular arrhythmias, some studies suggest these can be understood as instances of deterministic chaos.
Wait, so the problem itself might be a form of chaos?
Exactly, which is huge. Because if it's deterministic chaos, meaning it follows rules, however complex, it's not just random noise, then maybe, just maybe, it's controllable.
That opens up possibilities for treatment, right?
Big time. It has direct implications for therapeutic strategies.
So if these arrhythmias are a type of deterministic chaos, could we actually control them, like steer the chaos?
That's the fascinating thought. There's actually an approach for this, developed by physicists, called the Ott-Grabo-Georg approach, or OGY for short.
OGY, okay.
The idea is really clever. You used tiny, carefully timed nudges, little perturbations, to stabilize desirable but naturally unstable patterns of behavior that are already embedded within the chaotic system.
Okay, analogy time.
Think of trying to balance a pencil perfectly on its sharp tip. Seems impossible, right?
Yeah, completely unstable.
But if you could make tiny, precise, continuous adjustments at the base, you could theoretically keep it upright. The OGY method is kind of like that for chaotic systems. It makes desirable states accessible.
Wow, okay.
And the exciting part is applying this thinking to the heart. It could inspire completely new strategies. Maybe future pacemakers wouldn't just set a fixed rhythm.
What would they do?
They might use these tiny nudges to stabilize a healthy chaotic rhythm or gently guide the heart away from dangerous chaotic states like ventricular fibrillation. Imagine a pacemaker that learns and nudges your heart back towards healthy complexity.
That's incredible, using chaos theory to literally fix a chaotic heart problem. What about smaller scales? Inside our cells?
Oh, absolutely. We see these rhythms down at the cellular and molecular level too.
Like what?
Calcium oscillations inside cells. These fluctuations in calcium levels are fundamental. They control all sorts of complex cellular behaviors, and we see them in tons of different cell types.
And are they chaotic?
Well, often they're periodic, quite regular. But chaos and also something called bursting behavior have definitely been observed in calcium dynamics too.
Interesting. Anything else?
Another classic example is glycolysis. That's the main pathway cells use to get metabolic energy.
Right. Basic biology.
And the rhythms involved in glycolysis can also vary, sometimes orderly, sometimes chaotic. It shows these really complex oscillations and behaviors. It just seems to be a recurring theme, this dynamic dance between order and chaos across pretty much all scales of life.
It really is amazing, from cells to hearts. Okay, let's scale up again. The big one, the brain.
Ah, yes, the brain.
If chaos is beneficial, the brain seems like the ultimate place for it. How does this nonlinear symphony play out in our minds?
Well, the brain is the ultimate dynamic nonlinear system, isn't it? I mean, 86 billion neurons, 150 trillion connections or synapses.
Mind-boggling numbers.
Totally. And its activity is definitely not simple random noise. EEG signals, the electrical activity we measure from the scalp, they really show this beautifully.
They always look so messy on the screen.
They do. They look erratic. But underneath that surface, they exhibit clear, nonlinear, dynamic characteristics. And EEG is great for studying this. It's non-invasive, relatively easy to use, and has fantastic temporal resolution. It can capture brain changes really fast.
Okay, so if the brain's chaotic-looking activity isn't a mistake, what are the actual benefits? Why is brain chaos good?
Well, the richness that comes with chaos. seems to offer real advantages for what the brain needs to do. One paper puts it really well. It allows the system to quickly react to some new situation, changing conditions, and the response.
Adaptability again, flexibility.
Exactly. Think about it. A brain that was too rigid, too predictable. It would really struggle to learn, adapt, respond to novelty.
Yeah, you'd be stuck.
Right. There's this growing feeling, a consensus almost, that the future of understanding the brain, especially higher functions, will involve combining classical neuroscience with these newer ideas from nonlinear science. It really is like a dynamic symphony complex, flexible, sometimes orderly, sometimes chaotic.
Like a chaotic symphony. I like that. So what's the real-world evidence? Do EEG studies actually show this in action?
Oh yeah, so there's quite a lot now. Let's take cognition and intelligence. Some studies find correlations suggesting that higher intelligence might actually link up with a more complex, more sort of chaotic EEG structure.
Really? More chaos equals smarter?
In some studies, yeah. Participants whose brain signals showed more dynamic oscillating patterns tended to score higher on intelligence tests. It hints that maybe a more complex, adaptable brain is a more intelligent one.
That's fascinating. Again, so counterintuitive.
It really is. But then, look at the flip side. Cognitive load and fatigue.
What happens then?
We see the opposite trend, a decrease in chaos. So, for example, measures like sample entropy go down when people are doing really demanding mental tasks, like hard arithmetic.
So the brain becomes less complex when working hard.
It suggests the signals become more structured, maybe more focused, less exploratory. And when you get mentally fatigued, there's also a clear drop in the complexity of mental activity. The entropy goes down.
Like the brain is simplifying things to save energy.
That seems to be the interpretation. It really highlights that our cognitive resources are finite. Your brain kind of streamlines its operations when it's tired or under heavy load.
Okay, complexity is good for potential, for flexibility, but the brain pares it back when needed. What about people with highly specialized skills, like experts?
Specialized brains. Yeah, studies on people like professional pilots or dancers have found distinct ordered trends or fingerprints in their brain dynamics using these nonlinear measures.
Fingerprints, like unique patterns.
Kind of. For instance, pilots might consistently show a higher value for something called the Holder exponent in certain frequency bands, maybe beta waves, while dancers show it in different bands, perhaps gamma.
Reflecting their specific skills.
Exactly. These unique patterns seem to reflect those highly learned skills and specialized tasks. It's like their brain's dynamic patterns have been honed, optimized for performance in their specific domain. Their chaos is refined.
Neural fingerprint of skill. That's wild. What about broader states, like being asleep or under anesthesia?
Yeah, anesthesia and sleep studies really reinforce this link between complexity and healthy function. As anesthesia gets deeper, the complexity of the EEG signal decreases significantly. The symphony sort of quiets down.
Okay.
And similarly, sleep deprivation also leads to decreased chaotic behavior in brain signals. It consistently points to this idea: when biological systems are functionally compromised, whether by drugs or lack of sleep, they tend to show less complexity.
So a certain level of chaos seems essential for optimal function. It's a marker of health.
That seems to be the message, yes.
Okay, so if chaos helps us learn, adapt, stay healthy, could we actually design systems that use this? I'm thinking maybe brain-computer interfaces, controlling things with thoughts.
Yes. This is a huge and really exciting area for applying chaos theory. Take motor imagery, or MI, and brain-computer interfaces, BCIs.
Motor imagery, just thinking about moving.
Exactly. Just imagining movements activates the motor parts of the brain, even in people who have neuromuscular damage and can't actually move. And chaos theory measures are proving really crucial here. Why? Because they can help distinguish the brain signals for imagined tasks from signals when you're not imagining anything.
Detecting the intention.
Precisely. Detecting those unique chaotic signatures of intending to move. That's vital for BCIs that let people control wheelchairs, computers, prosthetic limbs just by thinking.
That could be absolutely life-changing technology. What about actual movement, like mastering a physical skill?
For motor movement and expertise, the findings are quite nuanced, actually. It's interesting.
How so?
Expert rifle shooters, for example. Studies found they demonstrate less reliance on complex brain activity during the act of shooting. Their correlation dimension, a measure of complexity, was lower.
Less complexity for experts?
Yeah, it suggests a highly refined, almost automatic execution. Their skill is so ingrained The brain doesn't need that exploratory chaos anymore. It's efficient mastery.
Okay, what about learners?
Amateurs, on the other hand, showed greater complexity linked to better performance.
So more chaos helps when you're learning.
It seems so. Increasing complexity might actually help you acquire the skill, up to a point. It's like you need the chaotic exploration phase to learn, then you refine it into efficient, maybe less complex mastery, finding that balance.
Chaos for learning, streamlining for mastery. Fascinating.
What about when we're just doing nothing, resting?
The resting state. Even when you're not doing any specific task, your brain is incredibly active. It's never truly off.
The default mode network and all that.
Right. And studies using these nonlinear methods are challenging some older ideas about brain microstates during rest.
What did they think before?
Kind of a simple winner-takes-all idea, where one brain region or network would dominate for a short period, then another.
And the chaos view.
It suggests something much more dynamic. Brain regions seem to be constantly competing and cooperating, exhibiting high complexity and chaotic behavior even at rest. It's a continuous, complex dance. Wow, okay, this has all been about understanding how chaos works in us, in biology. But you mentioned earlier, can we actually use this understanding to build new solutions? Can we sort of design with chaos?
Yes, and this is where we make that leap from observing nature to engineering solutions. These insights into biological complexity are directly inspiring a new generation of powerful optimization algorithms.
Optimization algorithms, finding the best solution to a problem.
Exactly. Finding the best way to do something incredibly complex, like what's the optimal dose schedule for a cancer drug, or the best settings for a diagnostic machine. These algorithms help find those answers.
And how does chaos fit in?
Well, traditionally, many algorithms were deterministic. They followed a strict, predictable path to find an answer, but maybe not the best one, especially if the problem landscape was bumpy.
Getting stuck in a suboptimal valley.
Precisely. But now we have these things called meta-heuristic algorithms. Many of them draw inspiration directly from nature, like how ants find food or birds flock, or how moths fly towards a light. Swarm intelligence.
Okay, swarm intelligence. And you mentioned we need lots of different algorithms. Why not just find the one perfect one?
That's a great point. There's actually a famous theorem in computer science called the no free lunch theorem.
No free lunch. Sounds ominous.
A little. But what it basically says is that no single optimization algorithm can be the best at solving all possible problems.
Yeah.
An algorithm that's great for one type of problem might be terrible for another.
So you need a diverse toolkit.
Exactly. And that theorem actually drives innovation. It encourages researchers to keep developing new algorithms tailored to different kinds of complex challenges.
Which leads us nicely to moth flame optimization, or MFO. What's the story there?
MFO is a perfect example of that nature-inspired approach. It's a swarm intelligence algorithm, and it's inspired by how moths navigate at night.
How do they navigate?
They tend to fly by keeping a constant angle relative to a distant light source, like the moon. That helps them fly in a straight line over long distances. But if there's a closer artificial light, like a candle flame or a porch light, they maintain that same fixed angle. But because the light is close, it makes them spiral inwards, closer and closer.
The classic moth drawn to a flame.
Exactly, and MFO borrows that idea. The moths in the algorithm represent potential solutions, and the flame represents the optimal solution they're searching for. They spiral towards the current best flame found so far.
Clever. And now, here comes the chaos, right? They didn't just stop with regular MFO.
Precisely. This is where it gets really interesting for our theme today. Researchers thought, what if we inject some chaos into this process? They explicitly incorporated chaotic mechanisms into MFO.
Wow.
They developed what's called a chaotic moth flame optimization algorithm, or CMFO. It uses things like chaotic maps to initialize the positions of the moths and to update their movement patterns. It introduces that beneficial variability, that exploratory power, into the algorithm search.
To help it avoid getting stuck.
Exactly. And this isn't just theoretical. This CMFO algorithm, it's already been used to optimize the parameters for a type of machine learning model called a kernel extreme learning machine, or KELM.
KELM, okay.
And they used this CMFO KELM system for actual medical diagnoses, including identifying breast cancer and Parkinson's disease from data.
Wow. So that's a direct line. Biological chaos inspires algorithmic chaos, which helps diagnose diseases.
It's a fantastic example of that translation.
But the story doesn't end there, does it? There's an even newer version.
That's right. Innovation keeps going. The next generation is an algorithm called BWMFO.
BWMFO. Okay, what do the extra letters mean?
They stand for the enhancements. BioInfo takes the basic MFO idea and gives the moths some serious upgrades. It adds 3 key strategies: a Gaussian barebone mechanism, a wormhole strategy, and an elimination strategy.
Whoa, wormholes. Elimination. Sounds intense.
It is pretty clever.
Yeah.
Think of it like giving the moth algorithm a super smart GPS. The Gaussian barebone part helps it converge faster and fine-tune its search near good solutions.
Okay, speeds things up. What about wormholes?
The wormhole strategy is cool. It allows the algorithm, or some of its moths, to essentially jump across the search space, like finding a shortcut. This really boosts its ability to explore globally and, crucially, helps it escape from those suboptimal valleys we talked about, local optima.
So it prevents getting stuck.
And elimination. The elimination strategy helps maintain diversity in the population of potential solutions. It periodically gets rid of the poorer performing moths, which speeds up convergence towards better solutions and keeps the search focused.
So these 3 things, faster convergence, jumping out of traps, and getting rid of bad solutions, they work together.
Exactly, they synergize. The combination significantly boosts the algorithm's performance, especially when you're dealing with really complex high-dimensional problems, the kind you often find in medical data.
And how is this one, BWMFO, being used in medicine?
Its main application so far is, again, optimizing the parameters for that Kelm machine learning model. This creates the BioInfo Kelm model.
Another step up.
A significant step up, designed specifically for medical diagnosis and prediction. And the key finding is its superior performance.
Better than the others. Better than CMFO.
Consistently better. When tested on real-world medical data sets, BioInfo Kelm achieved higher diagnostic accuracy and reliability compared to 5 other competing machine learning methods, including the previous chaos-enhanced one, CMFO Kelm.
Can you give us some numbers? Where did it shine?
Sure. For instance, on a well-known breast cancer dataset from Wisconsin, it had an accuracy of 98.17%.
That's incredibly high for diagnostic accuracy.
It is. And it showed similarly strong performance on datasets for colorectal cancer and predicting malignancy from mammograms. It wasn't just about overall accuracy either.
What else?
It consistently outperformed the others, including the original MFO Kelm and the CMFO Kelm in metrics like sensitivity.
Sensitivity. That's catching the cases you need to catch, right? The true positives.
Exactly. In medical diagnosis, correctly identifying people who do have the disease is absolutely critical. You don't want false negatives.
Yeah.
And BioInfo Kelm really excelled there.
That's a huge potential impact for patients. So let's just try and wrap this up. We started this deep dive looking at how chaos, the seemingly messy idea, is actually vital. It's a beneficial aspect of how our biology works.
Yeah, from the subtle variability in our heartbeats that signals adaptability, all the way up to the incredibly complex, dynamic computations happening in our brains. Healthy chaos.
And then we saw how those very concepts of variability, complex dynamics, adaptation are being deliberately harnessed, built into advanced algorithms.
Right, leading to breakthroughs like this BioInfo Kelm model, which seems to be able to diagnose serious diseases more accurately by using machine learning that's fine-tuned with these chaos-inspired optimization techniques.
It's really a powerful story, seeing how principles from nature connect directly to cutting-edge tech and medicine.
It really is. It shows how much we can learn by looking at the complexity of life, not just trying to simplify everything.
It definitely makes you think, doesn't it? How understanding and maybe even designing with chaos, embracing it, rather than always fighting for pure, rigid order, how that could unlock even more powerful insights, more solutions.
In medicine, for sure, but maybe in technology, even social systems. Who knows?
Yeah. What other surprising patterns, what other beneficial complexities might be waiting out there, just waiting to be uncovered in the complex systems all around us, makes you wonder.
Okay, there's a human in the loop. If you have any questions, go for it. Use the chat. If there's no questions, we might move on to development. Okay, I might need it on a bigger screen, so how shall we do it? How shall we do it? Yeah, we currently have 46 items to fix on the site. Can just the agents do all of it? Don't think so. They are not as good. So we have this one, for example. Well, this is already deployed and back, but it's not listed, so it's showing you. Is there audio? There meant to be audio for it. No, there isn't. Do you like the ECG sound? Quite nice. Is it? Is it working off this edge or that edge? Assume that should be 0. Okay. No, it's working off the right side, obviously. This is simulating a subject doing what? What's that? That's super odd. So 3 back should be, so it's a memory task meant to be doing while listening to music as well and trying to memorize. So you have 1 back, 3 back. It's like memorizing the previous letter or 2 letters back. So this one simulating how your heart and yeah, there's something wrong. Something's wrong. Can we get the agent to fix it? Fix it, fix it, fix it. Yeah, the demo meant to be cycling essentially through the different settings, different parameters in the game, I assume. Yeah. There's quite a few things that we could explain. Hey, which model should we use? 2.5? 2.5 Pro. So we're running this locally as well. Yes, eventually we will be deploying as well. We'll be deploying as well. So we essentially had Gemini doing the prototype, well, making this, and now we'll be trying to fine tune it in using other models. So perhaps Claude Sonnet 4? What do you think of Claude Sonnet 4? So there are quite a few issues with this web applications. First of all, it's not clear what's the difference between start, stop, and the play demo. The play demo also seemed to not run. It seemed to be stopping sometimes. I'm not sure if it meant to happen or not. And yeah, is there anything else wrong in the code? Can you look at the code real quick? Or not real quick? It will start talking to us.
Looking at your code, I can identify several issues. Main issues. Demo functionality is broken. The demo stops because it calls start-stop at the end, which stops the animation. Confusing UI. The start/stop button text and demo button behavior aren't clear. Demo timing issues. The demo sequence only has 2 steps but tries to run indefinitely.
Okay. I don't like this voice if you compare it to like Notebook LM. Well, you cannot really compare the two. It's not a fair comparison. So it's regenerated the whole code in the chat. Currently it's 472 lines of code. Should we generate a copy? We will generate a copy. $472, and this one is okay, much longer, 547. Start visualization, auto demo 20 seconds. So this will be cycling through the different, assume it should be in the explanation below. Yeah, and we have prompts for, making it ready for production. Where are the prompts? Oh, and there's no music. There is also no music. Start a new chat. Can you explain this web application in general terms without any code or any terminology? This is Claude Sonnet 3.7.
Understanding the physiological signal visualization web application. This is an interactive web application that creates a visual representation of how our body responds to different mental challenges and types of music. What it shows. The application displays 3 main bodily signals. Heart activity shows how your heartbeats change. Skin response shows changes in sweat levels that indicate stress or excitement. Breathing patterns shows how your breathing changes. At the top, it also displays letters that represent a memory task called NBAC, where you need to remember letters shown earlier. How it works. You can choose from 4 different combinations. Calm music with an easy memory task. Calm music with a difficult memory task. Exciting music with an easy memory task. Exciting music with a difficult memory task. The visualization shows how these different combinations affect your body signals. For example, exciting music or harder memory tasks typically increase heart rate and stress responses. Ways to use it. Manual mode. select a specific combination and press Start to see the visualization. Demo mode, press Auto Demo to automatically cycle through different combinations for 20 seconds. Audio option, you can turn on sound to hear a tone with each heartbeat. The app is meant to demonstrate how our bodies respond differently to varying levels of mental challenge and emotional stimulation, inspired by real scientific research data.
Okay. Yeah, that's pretty accurate, even though I don't like the voice. It's actually pretty accurate. What happened? Why did it stop? Not sure. So why is the EDA increasing? Why does the EDA has this spike when the new letter?
Looking at the code, the EDA, electrodermal activity, increases in the visualization for two main reasons. Different baseline levels for each condition.
Okay, can you explain without any code and without technical continuous sentences, why does the EDA spikes when there is a new letter appearing on the screen? What's the point of that?
Why EDA spikes when new letters appear? The EDA, skin conductance, spikes when a new letter appears on the screen because it mimics a real bodily response. When we encounter something that requires our attention, our body often has a small stress reaction. Our skin momentarily becomes more conductive due to slight sweating. It visualizes cognitive effort. The visualization is showing how our bodies respond to mental challenges. When we need to process and remember a new letter, it requires mental work. The spikes are proportional to difficulty. Notice that the spikes are larger in the 3 back conditions, where you need to remember letters from further back, compared to the 1 back conditions. This reflects how harder tasks create stronger physiological responses. It demonstrates multimodal interaction. The app is showing how different signals in our body interact when our brain processes information. It affects our autonomic nervous system. This feature helps make the simulation more realistic and educational, showing how even small mental tasks can produce measurable changes in our physiological state.
Okay, let's do Gemini 2.5 Pro. So going over the conversation above that we had, just in plain text without any code, can you explain how realistic it is and why the EDA, the skin conductivity, is changing so sharply instead of increasing and reducing more slowly? Sometimes won't let you finish talking.
You've made a very sharp observation. The way the EDA changes in the simulation is not entirely realistic, and that's a deliberate choice for the sake of demonstration. Why the changes are sharp, not slow. It's a simplified model asterisk. The simulation is designed to be a clear and simple illustration. It's not a perfect, complex biological model. For immediate feedback asterisk, when you change the condition from calm to exciting, the baseline EDA level jumps instantly. This is done so you can immediately see the effect of your choice. In reality, your body's arousal level would drift up or down much more slowly, over many seconds. To emphasize the point asterisk, the spikes that happen when a letter appears are also very quick. This makes the connection between the mental task, seeing the letter, and the body's reaction, the spike, very obvious. A real skin response is slower. It takes a couple of seconds to peak and then slowly fades. Realism versus clarity. Think of it like this. The simulation asterisk is like flipping a light switch. The change is instant and clear. A real body asterisk is more like a dimmer switch. The change is gradual and smooth. The application sacrifices perfect realism to make the underlying concepts easier to understand in a short amount of time. If the signals changed as slowly as they do in real life, it would be harder to see the cause and effect relationships during a quick demo.
Okay, shall we do which model? Which model shall we use? Let's do Claude Sonnet 4. Okay, so going over all the conversation above and the code in the web application, how can we improve the simulation, make it more realistic and accurate, but without making it way more complicated? Can you just generate a list of detailed instructions for doing it? Don't include any code or terminology in your response.
Improving the physiological signal simulation. Making EDA more realistic. Slower baseline changes. When switching between conditions, make the skin conductance drift gradually over 10 to 15 seconds instead of jumping immediately. Gentler stimulus responses. When a letter appears, make the spike rise more slowly, over 2 to 3 seconds, and fade out gradually, over 8 to 10 seconds, instead of the current sharp peak. Add natural drift. Include slow, random variations in the baseline that happen over 30 to 60 seconds to mimic natural body fluctuations. Improving heart rate patterns. Variable beat timing. Make the time between heartbeats slightly irregular, even within the same condition, to simulate natural heart rate variability. Gradual rate changes. When conditions change, have the heart rate slowly speed up or slow down over 20 to 30 seconds rather than changing instantly. Breathing influence. Make the heart rate speed up slightly during inhales and slow down during exhales to show the natural connection between breathing and heart rhythm. Enhancing breathing simulation. More natural patterns. Add slight irregularities to breathing depth and timing, with occasional deeper breaths or brief pauses. Stress-related changes. In high-stress conditions, make breathing occasionally become more shallow and rapid for short periods. Adding cross-signal interactions. Delayed responses. Make physiological changes happen with realistic delays. EDA responds first, within seconds, then heart rate, over 10 to 20 seconds, then breathing patterns adjust. Recovery periods. After high-stress conditions, show all signals slowly returning to calmer baselines over 1 to 2 minutes. Improving the cognitive task. Realistic stimulus timing. Vary the time between letters slightly, 1.5 to 2.5 seconds, instead of exactly every 2 seconds. Task difficulty feedback. In 3 back conditions, occasionally show stronger physiological responses to simulate when the task becomes particularly challenging. General enhancements. Individual variation. Add subtle random differences to how strongly each person's signals respond to the same conditions. Adaptation over time. Show signals gradually becoming less reactive as the person gets used to the task over several minutes. Natural noise. Add very subtle random fluctuations to all signals to mimic the natural noise present in real physiological measurements.
Okay, so make a copy of this file real quick, and we will engage an agent. Question. So in agent mode, you can use GPT-4.1, 4.0, Claude 3.5, 3.7, 4, which meant to be better at coding? I don't know. Gemini 2.5 Pro and 04 Mini. And that's in preview as well. I don't know what that means. Let's go for Claude Sonnet 4 agent mode. Okay, so based on a conversation above, can you change the current code, the current 547 lines of code, making sure it's still working and executing correctly so there's no errors? But yeah, essentially we want to go over the previous discussion and the different items for improving the simulation, web application, game, and improving the code accordingly. Well, let me finish. I have to speak faster.
I'll implement the improvements we discussed to make the physiological simulation more realistic. Let me update the code with gradual transitions, more natural variability, and better cross-signal interactions. Made changes.
Okay, so we're having Claude Sonnet 4 working as an agent, going over the code. Can you interact with it while the...
Made changes.
Made changes. It won't read the thing, will it?
Made changes.
Made changes.
Made changes.
Okay, we already can see the changes. The respiratory thing changed, the EDA have changed. The ECG looks weird.
Made changes.
Made changes. Why the ECG looks weird?
Made changes.
Every time it's making changes, it's
Now I'll test the application to make sure everything is working correctly.
Okay, we can cancel that. Okay, so that was Claude Sonnet 4. We'll keep the changes. Now let's do Gemini 2.5 Pro. And and just describe the issues. Okay, so we have a human testing the application, so we have it running locally. I can see what is it doing and the changes made. Yes, the changes were made okay from previous, as based on the previous discussion, but now the ECG seem to be flatlining and the EDA is changing, but not very much amplitude-wise. If there's any other issues with the code or something is incomplete, can you go over it and find any issues and improve the code? Right, now you have more fluctuation in EDA, which is good.
Of course, it looks like the previous changes introduced a few subtle issues that made the simulation less dynamic.
Right.
The ECG flatlining was caused by the gradual transition logic moving the heart rate towards its target too slowly, and the EDA signal's low amplitude was due to the spike calculation being a bit too conservative. I've made the following improvements to address these problems and enhance the simulation's realism. Repaired ECG signal *. I've adjusted the transition logic to allow the heart rate, current ECG BPM, to change more quickly when a new condition is selected. This will prevent the flatlining issue and ensure the heart rate realistically adapts. Increased EDA amplitude *. I've increased the multiplier for the EDA spike, EDA spike value, to make the responses to new letters more pronounced and visually clear, better reflecting a real physiological reaction. Smoother transitions *. The rate at which the signals transition to their new baseline levels is now more consistent and smoother, providing a more natural feel. Code cleanup *. I removed an unused variable, current condition, to keep the code tidy and prevent any potential confusion. I will now apply these changes to the index.html file. Made changes. Of course, it looks like the previous changes, while adding realism, introduced a couple of bugs that caused the ECG to flatline and the EDA signal to be too weak. I've identified and fixed these issues. Here are the changes I'll make. Fix the ECG signal *. The calculation for the heartbeat shape was incorrect, causing it to draw a flat line.
Okay.
I will correct the timing logic to ensure the QRS complex, the main spike of the heartbeat, and the T wave are drawn correctly. Boost EDA amplitude *. The EDA signal was being dampened too much. I'll adjust the amplitude of the EDA signal to make the changes more visible and realistic, ensuring the spikes in response to stimuli are clearly represented. Refine signal smoothing *. The gradual transitions between states were a bit too slow, making the signal appear sluggish. I'll adjust the smoothing factors so that the transitions are still gradual but feel more responsive. Code cleanup *. I'll remove an unused variable, current condition, to keep the code clean and efficient. I will now apply these fixes to the code. Made changes. Of course, it looks like there were a few issues.
Okay, I'm not sure why it's reading the same thing again. That's just how the agent works. That's Gemini 2.5 Pro in agent mode. It made a huge improvement though, that's for sure. So now the demo mode should be cycling through calm music 1 back, exciting music 3 back, just doing random, what else? Calm music 3 back, and there should be a 4th one, exciting music 1 back, so it shows you the difference between them. Yeah, well, it did what we asked it to do. So it's very nice that way. Very nice that way. I'm not sure. Do you know how to improve it any further? I don't know. Okay, it's much better than what we had. That's for sure. So remove the previous version. We will remove the previous version. It might be easier to hear. So this is the heart rate for ECG for the exciting music 3 back task. If we turn it to the easiest task, yeah, the heart rate is slower. The EDA, so essentially stress level, is lower. Don't know what's happening to the respirations, seem to be the same. Yeah. Let's do ask 2.5. Just text response, no code or terminology. Do we have any issues in the major issues? Do we have any major issues in the code? And also, how would you improve the simulation? Can you also ask some questions about it that are currently not answered, or potential future direction, just in the chat, continuous sentences?
There are a few things in the code that could cause problems, mainly that the speed of the simulation is tied to your screen's refresh rate, which can make it behave differently on different computers. Also, the way the audio is handled by creating a new sound for every single heartbeat might not be the most efficient way to do it over long periods. To make the simulation feel more real, you could make the different signals influence each other more directly, so a spike in stress would not only affect the sweat response but also cause a noticeable change in heart rate and breathing pattern at the same time. Adding small, random imperfections or noise to the data lines would also make them look less perfect and more like real-world measurements. It would also be interesting if the simulation could react to simulated user actions, like getting an answer wrong in a cognitive task, which would realistically cause a brief stress response in the signals. This leads to some questions about the project's goals. For instance, what is the ultimate purpose of this visualization? Is it for education, data exploration, or something else? Are you planning to model how factors like caffeine, fatigue, or time of day might affect these physiological responses? It would also be interesting to consider how you might visually represent the user's performance on the NBAC task itself and show how that performance correlates with the physiological data in real time.
Yeah, those are really good questions. We'll have to think about it. We will have to think about it. What if we do Claude 4? The same response. Okay, we did the same, used the same prompt. Well, once for Gemini, second time for Claude. Now I want to use like GPT-4o to combine. Last two responses.
The code has a few potential issues that could impact its performance and realism. One major concern is that the simulation's timing is tied to the browser's refresh rate through request animation frame, which could lead to inconsistent behavior across devices with different refresh rates. Additionally, the audio handling, where a new oscillator is created for every heartbeat, might cause memory or performance issues during extended use, especially on less powerful devices. To improve the simulation, you could make the physiological signals interact more dynamically, reflecting real-world dependencies like how breathing affects heart rate variability or how stress causes simultaneous changes across multiple signals. Adding subtle noise or imperfections to the data would make it appear more realistic. Gradual adaptation over time, where the simulated user becomes less reactive to stress, could also enhance realism. Furthermore, making the simulation interactive, allowing users to perform tasks and see how their actions influence the data, would make it more engaging and educational. This raises some interesting questions about the project's goals and future directions. What is the primary purpose of this simulation? Education, research, or entertainment? Are there plans to validate the simulation against real physiological data to ensure accuracy? How might individual differences, such as baseline heart rate or stress reactivity, be incorporated? Could environmental factors like fatigue, caffeine, or time of day be simulated to add depth? Finally, how could the visualization be expanded to include additional data types, such as brain activity, or allow users to annotate events and explore correlations in real time? These considerations could guide the next steps in development.
Okay, so now we have Claude Sonnet 4 is agent, so we want to fix and update the code based on the previous discussion. Now any future any feature and how the changes should be described in the text below the canvas. Now we also, for production purposes, we want the educational, interactive, and accurate simulation. The game canvas should be around 80% of the viewable height. A text web app overview, how to use feature direction below the canvas. It should work with keyboard, mouse, and touch. Should work on all screen types. And all screen sizes. Yeah, if you want to use, we have a prompt of like not using Tailwind and Google APIs, but that's fine. You can use whatever you want. And we have this showcasing the simulation capability. We have the demo button. That's already working. So we have 640 lines of code. We have a copy, a local copy of it as well. Yeah, we need to add I don't know how to specify it, but the keyboard shortcuts don't currently work. Okay, we'll have to finish in a sec. If there's any human who would likes to interact or ask any questions, go for it. Otherwise, we'll continue next time. Okay, yeah, that's based on this data set. How to use signal guide, physiological accuracy, adaptation effects. Yeah, we could be adding FNIs and machine learning biofeedback. Yeah, many different things. For now, we'll just keep it simple. Keep it simple. Still making changes, is it? Fixing the timing issue. Updating the information section. Thank you very much. Okay, stuffed something up, did you? No, it's still working. The keyboard shortcuts don't work. Might get rid of them. What? What happened to the respiration. Yeah, it added some variability and noise and stuff. Okay.
I'll fix and improve the physiological simulation based on our discussion, making it more educational, interactive, and accurate while ensuring it works across all devices and screen sizes. Made changes. Made changes. Made changes. Now I'll update the HTML structure to include the performance overlay and improve the layout. Made changes. Now I'll update the information section with better structure. Made changes. Now I need to update the JavaScript to fix the timing issues and add interactive features. Made changes. Made changes. Now I'll update the simulation logic to fix timing issues and make it more accurate. Made changes. Now I need to add the new helper functions and update the animation loop. Made changes. Now I need to add the event listeners for keyboard and mouse/touch interactions. Made changes. Finally, I need to update the initialization and start function. Made changes. Made changes. Perfect. I've successfully updated the physiological simulation to address all the issues discussed and implement the requested improvements. Here's a summary of what I've fixed and enhanced. Major issues fixed. Timing independence. Replaced frame-based timing with delta time calculations to ensure consistent behavior across different refresh rates. Audio optimization. Reduced audio volume and duration to prevent performance issues during long sessions. Responsive design. Canvas now uses 80% of viewport height with proper responsive layout.
Let's get unlike this sound. Anyway, we added so there will be like keyboard responses that you can actually, you know, do the task yourself. Obviously, the measurements are not of you; they're just being simulated. They could be simulated based on your responses, I think. So yeah, we'll have to go over it multiple times. I'll have to do it next time. So everything we do is available on this website, BioniChaos.com. Go check it out. Let us know what you think. It's currently under development, so any feedback is more than welcome. And I'll see you next time. Bye.